It's 9:30 on mine.
Oh, okay. Alrighty. Yes, I'm Peter Lauritsen. I'm one of the developers of CAM, and I'd like to talk about idealized testing of the new die cores we have in CAM and CESM. I really miss seeing all of you and discussing with you in the breaks, because I learned so much with talking to you. So hopefully that will happen. Hopefully at next AMWG. So as you've been hearing yesterday, if you tuned in, the CSM community, so being the steering committee, the advisory board, the MWG community, you guys, we're starting to having a discussion about how to move forward on dynamical cores for our mainstream 1 degree simulation for climate and climate change applications used, for example, for CMIP7. And as you probably also know is we basically have 3 choices in here. We have the spectral element dynamical core that's the furthest along in terms of support within CESM. It has a variant called SEC-SLAM where we use a different transport scheme and run physics on a different grid than the die core. Then we have NOAA GFDL's FE3 die core that we have run all the way to coupled configurations. And then we have MPAS that we have tested pretty rigorously in idealized setups, and we are now pretty close to having AMIP running. So I'd just like to point out that we're pretty close to a pretty major achievement within CESM, being that we can, with a change in the argument in our CSM scripts, you can run 3 state-of-the-art dynamical cores seamlessly within CESM. So that means you have diagnostics coded up in physics. They work seamlessly across die cores. It also means that CESM is a really versatile tool for dynamical core research. So please write proposals. Please use these options and do science with it. And it also means we have a pretty broad range of solvers and grids in the CESM. So in some sense, we do not have all our eggs in one basket at this point in the game. So when having these different die cores, we obviously need to evaluate them. And a couple of years ago, we made the argument that we should look at dynamical core intrinsic properties first. So that means you're running the die core in some more simpler setups, so it's easier to assess cause and effect. Whereas when you run with full physics, the physics can mask a lot of stuff going on, making it harder to understand what is happening. So I presented an idealized test suite back in 2018, winter AMWG meeting. And we proposed to look at these different properties listed here. And we're pretty close to having that wrapped up. So after Christiana's talk today, we're going to have a discussion about what we call step 2 in this evaluation process. But just in one sentence, we'd like to run all the different die cores with the new vertical resolution that Isla Simpson talked about. And we're going to start looking at AMIP configuration. But there'll be more about that in half an hour or so. Also like to just make people aware that there is usually a lot of back and forth between running CSM simpler models and full AMIP configurations. So for example, when we run AMIP, we may want to change the sponge layer diffusion. We may want to change time steps for stability and efficiency. There might be algorithm changes, such as what is going on with spectral elements right now. And also there's constantly code optimizations in different parts of the model. So our results of the intrinsic property evaluation may change somewhat due to what's happening in step 2 of this process. So what we're looking at is we're interested in computational performance at 1 degree, both in terms of what's the throughput with different core counts, and also what's the efficiency of the model as we add more tracers to the configuration. We then also been looking quite extensively at tracer transport characteristics. we've been looking at angular momentum conservation properties of the dicore. Then we've also been looking at running the dicores in an idealized setting using real-world topography, and I found it particularly useful to run with a very simple forcing called Hell-Suarez forcing. And then last but not least, we're also looking at the total energy budget in CAM when using these different dynamical cores, and those tests are mainly happening with full physics. So I don't have time to go into detail of all of these kinds of tests, but I'm just going to pick a couple of them. So let me first talk about tracer transport characteristics. So the setup we're using here is a moist baroclinic wave developed by Paul Ulrich that's been used extensively in the DC MIP summer schools. What we do is we add a bunch of inert tracers to this baroclinic wave, as well as to reactive chlorine species. Down here, you see what the surface pressure looks like at day 10 of this simulation. And then on the right here, you have the precipitation rates. So what we're doing is that we've coded up a bunch of diagnostics to look at tracer transport scheme characteristics. And the things that we're looking at do not require a reference solution, which is very convenient. So the things we're looking at, though, we're keeping an eye on mass conservation. There's no problem there with all the different dicores. We're looking at shape preservation. So does the transport scheme extend the range of the initial range of mixing ratios for the different distributions? So if this happens, this is spurious. We're looking at various mixings, both mixing of one tracer and mixing of two nonlinearly correlated tracers, as well as how well do the transport scheme preserve, a sum of tracers. And all of this is directed towards aerosol modeling and chemistry modeling. And then we have one set of species that actually do nonlinearly interact with each other. So it's kind of a forced simplified chemistry problem we're looking at. I'm just going to show results for the mixing between two nonlinearly correlated tracers. So what we do is we throw these two distributions into the initial condition. So, and these two species are nonlinearly correlated. So that means that if you plot mixing ratio 1 against mixing ratio 2, then they all line up on this parabolic curve here. And in a perfect scheme would let all the points here just remain on this curve as the simulation proceeds. However, truncation errors will in general move the points away from this curve. And from theory, we know that if the truncation errors resemble mixing happening in the real atmosphere, then they have to move into this red area here called the convex hull. Anything else is unphysical, doesn't happen in nature. And we categorize those into unmixing errors within the range of the initial distribution, and then overshooting, where we're actually expanding the range of the initial distribution. So on the right-hand side here, I don't remember which dicore it is, but this is what the distribution looked at 850 hectopascal at day 10. So the initial distribution has deformed into thin filaments and challenging the transport scheme at the grid scale. This is what you get from the different dicores at day 10. What you see is that most of the mixing is real mixing, which is good. And then most of the dicores, all dicores, will produce some level of unmixing, what you see right here. And then some of them also produce overshooting. So that's a little hard to see on the scatter plot. So you can also quantify the different types of mixing, which is shown on these plots here. Let's just go right to plot B here, where you have real mixing error norm as a function of days for the different dicores. And here we see that the finite volume core that we're running as a reference has the least amount of real mixing, but we do have to keep in mind that with the lat long grid, it has a higher resolution than all the other more uniform resolution grids that we're looking at. So that's probably the reason why it's doing a lot better here. Then CSLAM is next in line in terms of mixing, and then we have MPAS and then FE3 and SE on top of each other. In terms of unmixing on plot C here, we see the finite volume and CESM have the least amount of unmixing, and then the other dicores have more. And in terms of overshooting, CESM and MPAS have none at all, and then the other dicores have some level of overshooting. And again, if you change the details of the limiters in these transport schemes here, or change time steps, you get different solutions. So these metrics here are quite sensitive to the details of the transport scheme. The other thing I'd like to show results for, and this is inspired by Rich's presentation yesterday, where he was showing results of excessive precip over the Andes, and it has likely something to do with the dynamical core and its vertical coordinate. So what I'm showing here is on the right-hand side here, this is results from SEC-SLAM using Hell-Suarez forcing for putting in real-world topography. So it shows the climatology of the 500 millibar vertical velocity. And then on the left-hand side here, I'm showing vertical velocity for a 1-year AMIP simulation, so a real-world simulation on the right. And the reason I'm showing them side by side is just to show what I believe is the usefulness of actually running this test here. So what we're seeing is, compared to other dicores, is we have excessive vertical velocities over the northern part of the Andes and over South America, over Africa, as well as the Himalayas. And these noise issues shows up in both configurations, and maybe a little bit less in AMIP because we have the interaction with the boundary layer schemes that introduces some level of mixing. So this result here is for the 2.2 release of spectral elements. And DOE with Mark Taylor and us at NCAR have been worried about these problems here and tried to come up with solutions with them. And quite recently with Mark Taylor, we found a really nice way of alleviating this problem, namely by introducing reference profiles in the viscosity operator and some changes to the pressure gradient force. And now you see we're really removing a lot of the spurious vertical velocities over the northern part of the Andes, Africa, and the Himalayas. So you're running this test here with all the different dicores to keep an eye on these kinds of errors as we believe that can impact the AMIP simulations in a negative way. And I think I'm running out of time here. So for those of you who are interested, there are extra slides in this slide deck going through all the other tracer transport metrics, as well as the momentum conservation results, and some of the total energy results are in here as well. So with that, I'll be happy to take questions.
Hi, Peter. Thank you very much. Sean is asking a question, which I would also repeat. On the last two slides, what is the difference between the left and the right plots?
Let's see.
I think he means the topography. Yeah. Okay.
So on the right-hand side, both left and right see the same real-world topography, but on the right-hand side here, I'm just using Hell-Suarez forcing, meaning that we're relaxing temperature to a static climatological profile. And then there's some simple representation of boundary layer diffusion. Mm-hmm. And on the left-hand side here, you see a full CAM-6 simulation. And here it's just average from a 1-year simulation.
Okay, and so both plots here show the impact of the new PG, the new pressure gradient formulation, compared to the previous slide. Yeah,
correct. So in the previous slide here, we all right. Yeah, we're using some methods to alleviate the noise, but obviously we've improved it greatly here with the new modifications. So yeah, so left and right use the same modifications in the dicor.
Okay. All right, thank you. Chris Cruz asks, how do you originally conclude that the small scale omegas over topography are spurious?
Yeah, that's a good question. So I don't have a plot here, but we've also run a 1/4 degree simulation where we smooth the topography as much as we do in the 1 degree, believing that then the dynamical core would have converged further to the quote unquote true solution. And when we look at that, like we don't have this spurious small scale, let me go back, spurious small scale noise here over Africa and Northern Andes. And similarly, when we look at the ensemble, like all the different dicores, they all agree at 1 degree that you don't have this kind of noise. So that's how we're attributing these vertical velocities for being spurious.
Okay, thanks.
Oh. So we're more looking at noise issues rather than are the vertical velocities right in a certain sense.
Okay, thank you, Peter. I think it's 9:45, so we'll move on to Christiana's talk, which the theme of three. So Christiana, why don't you go ahead?
Do you see the slide deck?
Yes.
Yes. Okay. So this is actually, Peter gave me a perfect introduction, and I will basically hit on a few aspects that he just mentioned and even shed more light on this noise issue over topography. So what this talk is about, it's about a new dynamical core test case, and we are adding topography to a moist baroclinic wave. And this is similar to things Peter just mentioned. This is work with my student, Owen Huge. So overarching questions. How well is the topography forcing simulated in the dynamical cores? And now we look at them in isolation with Kessler physics. These are moist dynamical core runs. What is the impact of that moisture on these waves that are triggered by topography? How does the shape and the peak height of the topography impact the flow, even the orientation of the ridges, the mountain ridges? And does the impact of topography differ when you look at different dynamical cores? And yeah, you can ask even more questions. What can we learn about the choice of the vertical coordinate system on the physics dynamics coupling? And I hit on a few of these questions. I want to put this into perspective. This is kind of similar to Peter's motivation on talk. I put this here into the CSM simpler model framework. And for those who are not familiar with that, here's a link to the so-called simpler model hierarchy that I contributed to with a few of the test cases, but as you see, and this is here a depiction of the hierarchy, it's quite extensive now. We are mostly, Peter and I are mostly playing here in this DCMIP arena, maybe even in the dry or moist heterogeneous test case, which would be here captured in the dry dynamical core. But there are extensions. Kevin worked on radiative convective equilibrium models. There's, of course, Upper Planet and the real world. What has been missing so far, Peter showed an exception, but most of these simple model test cases do not have topography, and this is our contribution. So we are now adding an element to this dynamical core test case hierarchy with this research. And this was inspired by atmospheric rivers. For those who are not familiar with atmospheric rivers, here's a depiction of the latest that hit California. I want to just point you here. This is a total water, precipitate water. And this is the atmospheric river here, this band that hit California just 2 weeks ago. You also see this a little clearer here in the integrated water vapor. This is this very narrow and long band, and also in the integrated vapor transport. So atmospheric rivers are these features that hit topography upon landfall here along the coastline, California, for example. And this leads to huge rain dumps. And this is really our inspiration. We want to kind of mimic this with this test case. So it's a relevant test case for the community. The configurations we look at come from CSM, and in particular, I will show you some example results here from all 4 dicores, which is spectral element, finite volume cubed sphere, and also MPAS. And this was a standalone repository, not yet the one in CSM. And for those who are familiar with the simpler model hierarchy, this is a F Kessler concept. It is a warm rain physics scheme. where we only let it rain. There was no evaporation or even surface fluxes. And the analytic initial conditions are inspired by our DCMIP 2016 dry and moist dynamical core test case, which was a baroclinic wave documented here in Ulrich. So we added topography and we removed the usually used initial zonal wind perturbation. So let me give you an example how these initial conditions look. So this is zonal wind, temperature, and Q, a latitude, height cross section. And here you see now the mountain range in that depiction. Here you see it even clearer. This is the surface height. And we picked a really long ridge and narrow ridge. And you see actually two mountain range. The corresponding pressure, surface pressure, needs to be balanced. So this is now the adjustment of the surface pressure to these ridges. And we took some inspiration from real topography, and especially here the Andes or the Rocky Mountains that are long, narrow ridges. A little bit, well, the orientations are a little different here, but in general, we are mimicking those profiles. So in order to just give you an idea how these flow fields look, this is surface pressure, this precipitation, the temperature, and precipitable water. This is now a loop over 10 days. So we are here day 5. You see the evolution here of the baroclinic wave in the sea level pressure field. And with that, especially with the frontal zones that you see in the temperature, come these rain bands. You also see really sharp gradients. Let me just start this again. You see really sharp, after a while, in the precipitable water, sharp gradients here that really pull up the tropical moisture here into the mid-latitudes. You also see that this just hit the mountain, which one of the mountains located here. So we are also looking here at the interaction of the rain with topography. This is the SE model, and there is a caveat, and this kind of goes back to the noise issue that Peter just showed. Here we are looking at omega, the vertical velocity. And after a while, you see a lot of ringing. You kind of see it now coming here, which is a small scale noise. You also see actually a large propagating gravity wave. And I'm really curious to learn what the modifications are in the SE dicore to see whether, when you watch this wave traveling, it's a really high speed gravity wave, which comes from the initial imbalance here over the topography. And this doesn't go away over 10 days. Very curious because the other models do fade it out. So we see, okay, noise and a big gravity wave here in the 850 vertical velocity field. Okay, so just snapshots now, and these are example snapshots of the potential application areas. Start with a moist versus a dry configuration. And you can ask the question, how is moisture contributing or impacting the evolution of a baroclinic wave? And it's striking how much it does. So we are seeing now results from SE at 50 kilometer resolution, moist versus dry. Identical mountain configuration, just the moisture is present in this simulation. And after 5 days, when really the wave, the first wave here hits the mountain, we see pressure differences, sea level pressure by over 25 hectopascal. I think this is really striking. And the only difference is presence of moisture and rain. Okay, and this is really a quick walkthrough to some potential things you want to look at. Another potential area is physics dynamics coupling, and this is now again the SE dynamical core. And as some of you might know, we can vary the way we couple physics and dynamics. This is determined by a nameless parameter called F-type. The default is down here actually, which is called hybrid, and this means that we dribble in tendencies for U and V and temperature, but we do a big step for the adjustments of moisture. And this leads, as I said, day 5, vertically average omega even leads to the ringing that we saw. And this is really striking. It's even worse if you have sudden adjustments, and this means every 900 seconds, this is a physics time step, we adjust all variables at once, and this is really unhealthy. If we dribble everything, including the moisture, we diminish this. And in dry, of course, there is no moisture dribbling or sudden adjustment. There is nothing, there's no noise visible here in that simulation. We can look a little further into this. This is the simulation I just showed you with some of the settings that you can choose in the SE dicore. And this means that the physics time step is 900 seconds, dynamics time step is 150 seconds. If you don't do that, if you just use 150 seconds for everything, die-core and physics, the noise also goes away. So there is this interesting interplay between physics and dynamics. I bet you can actually increase diffusion and also get rid of this noise, which we haven't done yet. It's just an assumption. Okay. Another application example is a die-core intercomparison. And you can start again by looking at sea level pressure as one of the measures. So this is the sea level pressure here from SE, FV. These are all 50-kilometer resolutions. This is FE3 and MPAS. And just snapshots here of sea level pressure. It looks similar, yes, at first sight. But when you really look at it closer, and this is now a timeline of the evolution of sea level pressure, there are striking differences, especially here in the color. For example, the FE3 dynamical core ends up with 950 some hectopascal versus the others, which are down here at 941. So it's about 11 hectopascal difference due to the choice of the die-core. And this needs to be looked at a little more, but I thought that's interesting. The black curve is dry, and we do see that it's not intensifying as quickly. Well, other fields you might be looking at are precipitation rates and precipitable water at day 5. The mountains are located here and here. I left them out, otherwise you don't see anything. And here you can really dive into these differences, especially, let me highlight those. The first wave on rain band is not impacted by topography. It was triggered by topography, but it's not impacted, it doesn't hit anything. And this is the impacted one that hit topography at day 5. So you can, compare these two. You can, of course, compare the die-cores. You do see differences, of course, here also in these mid bands, pretty striking actually, and here in MPAS. So this is another example how to look at it. Or coming back here to vertical velocity and potential noise, this is a simulation we saw here from the SE die-core, and other die-cores don't have that. So interesting. Again, this may be battled with diffusion, well, smaller time step, but the other die-cores didn't have it from the get-go. A closer look also, and this is again topography, this is omega, the vertical velocity at 850. I mentioned again, this is a simulation we saw as a movie. We saw these big traveling gravity waves here at day 5. They are down here and here. Let me highlight these guys. They are not present in any of the other die-cores. So this is intriguing, and I need to get in touch with Peter to see what the newest modifications actually get rid of this. This has caused all die-cores have a little bit of that gravity wave due to the initial imbalance, but SE is the only one that keeps it persistently for 10 days. So the others faded out. Okay, so you saw some snapshots of potential application areas, how we can look at dynamical cores with topography. And I think this was, or it has been neglected. It's an additional element in the simpler model test hierarchy. So it helps us answer some fundamental dynamics questions. For example, I showed you can, examples here, you can look at moist versus dry dynamics. The impact of modern shape, size, and peak heights. I didn't show that on the clouds. And you can even go after topographic gravity wave studies. What I focused a little bit on in this talk was the numerical interplay, the physics dynamics coupling. We can take a look at hydrostatic versus non-hydrostatic designs, whether they matter, diffusion characteristics, and also how the simulation of clouds and rain is impacted by the topography. And here we started actually looking at probably 15 different topography profiles before we settled on the one I showed you. But we have 2 papers in preparation now. One is a characteristic of the test case that I showed you, and one will be this more fundamental view at the impact of topography on rain. And this closes my presentation.
Thanks, Christiana. That's very interesting. We have two questions right now on the chat from Adam. Adam, do you just want to ask your question?
Yeah, I guess I'd almost revise it. I'm wondering what your motivation for using half a degree grids instead of 1 degree grids for this study
The 1
was.
degree looks very similar. We do have that. So we actually went to a 1/4 degree as well, 25 kilometers. Here, I just wanted to be kind of in the mid-range of our investigation. Again, the 1 degree looks similar.
Okay, thanks.
And that was actually a design decision. So we wanted to have a mountain shape that is resolvable at the 1 degree, because 1 degree is still kind of our workhorse when it comes to climate predictions. So with our shape of the topography, when you just very briefly go back here, this is, as you see, goes over, well, let me say 10-ish or so, maybe more degrees here. It's a narrow band, but it's still resolvable at the 1 degree.
Okay.
And thank you. At Chris, we have a few more questions popping up here. Chris Cruz would like to know if you used any drag parameterizations like Bell-Yars or orographic gravity wave drag.
No, this is a plain dynamical core with just Kessler physics as the only physical parameterization process.
Okay.
But it could be added.
Yeah. Right. Hanli is wondering about the kinetic energy spectrum in the spectral element core. Is it shallower than it is in the others?
Oh, I didn't look at this. Good question. Typically, so I can't comment on this with topography. I can comment on this without topography, where we looked at it. It is not shallower, no. So it compares quite well, actually, to the other die cores.
Okay. And I'll let Thomas Toniazzo also has a question. I'll let him give it.
Thank you, Julio. It's just a small comment that I noticed that in several occasions, actually, that FV3 tends to generate patterns where the cube faces meeting the vertices. Yeah. But this doesn't seem to be a problem in a COR impasse. Is that right?
Not a problem in which model? CE? Which one? In
so
CSM?
In SE or in impasse, I only see this in FV3.
Let me point you to. Yeah, you saw. I didn't really comment on this. Yeah, you do see some of the noise that Thomas referred to here is the FV3 die core. We do see this is wave number 4. It's also present up here. It's of course not visible here in this range. Yeah, this is definitely noise triggered by the FV3 cubed spheres, the corner points. Yes, it's not a visible feature, at least not obvious here in the SE die core. Also, MPAS doesn't have a signature of its built-in wave number 5 pattern, at least not in this depiction. I guess I'm cautious. This is brand new. This result is from CSM 2.2. This has been released. It's still in the making. There are a few adjustments that happen as we speak. I also needed to remap this from the cube sphere to the Lagrange grid to have that depiction. So there may be a few things that should be looked at before we really claim. But yeah, you're right. I think it's obvious that FV3 has more signature of the cubed sphere than SE.
And Peter has raised his thank you. Peter Lauritsen has raised his hand.
Yeah, just to respond to Thomas as well. I'm seeing noise in omega with FV3 as well in my setup. And then I just wanted to quickly mention, I think the noise you're seeing with spectral element could be related to the sponge. We've had a lot of stability issues with higher tops, and the Del2 sponge or the Laplacian sponge has not been that successful. So what we've had success with is doing hyperdiffusion, like increasing the hyperdiffusion coefficients in the sponge. So that might solve this problem or not.
Are you referring to the smaller scale noise or the?
Yeah, I'm referring to these gravity waves that are just not dammed out, and they might just be bouncing off the sponge or off the model top.
Yeah, I'm intrigued to learn whether your latest modifications will actually get rid of these guys, which are striking.
Yeah, let's do it.
Yep.
So I'll take my prerogative to make one question, even though we're a little bit over time here. I thought it was interesting that in your comparisons of the various forms of dribbling tendencies, just dropping instantaneously the moisture tendency still produces noise, even though moisture is it's just a passive tracer as far as the dichord is concerned, right? So what?
No, in this, no, there's this coupling between moisture and the dynamical core. So whenever you remove moisture via rain, it couples back into the dichord.
Okay, but does that happen during the dichord time step?
No, this of course happens at the physics time step.
Right.
Well, there's still your computation of virtual potential temperature that has the moisture in it.
Right.
So I don't think it's decoupled.
Okay, thanks. Thank you. All right, if there, yeah, I think.
Should I stop sharing or?
Sure. It doesn't look like there are any more questions in the chat, and I think it's time for us to move to the discussion of the dichord selection process. So I think.
So Ayla and I have put together some slides we would like to present to get the discussion going, if that works for you.
Yeah.
Okay.
You guys, the two of you and Christiana are in charge. So go ahead.
Sorry, let me just make sure I've got the right presentations. Okay, so yeah, I'll just go quickly through this process that has been proposed for selecting the dichord for the next workhorse version of CESM before we start discussing this. So as we've already heard this morning, there are 3 potential dichords that can be used. And to be clear, this is a selection of the dichord for the next kind of CMIP type applications, the workhorse version of the model, but all of the other dichords that are not selected would still be within CESM and can be used for other applications. And so there are kind of, multiple facets of dichord performance to be considered. And the first is this kind of inherent properties of the dichord that Peter already talked about this morning. And so assessment of each of them in terms of these inherent properties is already well underway. And I think Peter's will either writing it up or will soon be writing it up. And so then the next phase is to look at them all in more kind of comprehensive climate type simulations. And so that's what we're about to embark on and kind of the plan that we'll lay out here for doing that. And the idea is that this first phase will just be looking at AMIT mode simulations. And then we'll kind of regroup and see what have we learned from this and decide how to proceed with the next phases, which would be doing other coupled simulations or perhaps interactive chemistry simulations. These are yet to be defined how exactly the next phase is going to go. So the plan for the second phase is kind of inspired by what was done with the vertical resolution, is to propose a kind of similar protocol here where we'll have groups of people that are focused on assessing the dichord in AMIP simulations. And so we'll use the historical period with kind of whatever is the CAM development physics at the time that we really start to do this. And the plan will be to use the vertical grid with the 80-kilometer top and the enhanced boundary layer resolution that is planned for the vertical grid for the next workhorse version of CESM. And so obviously in this process, we wouldn't have the chance to tune up all of the dichords to perfection. The plan is that all 3 of them will receive similar attention when it comes to tuning, and we'll look at basic things that can be easily tuned quickly and things that we expect will be sensitive to the dichord, like in particular aspects of stratospheric dynamics that can be tuned to some extent with gravity wave drag. And so the idea is we'd have some time where we're doing that tuning with just short simulations to make sure we can get each of the dicores to run properly and give them the best chance of simulating these things well. So when it comes to looking at the diagnostics, there's many things to look at, but we'll be focusing on things that are expected to be impacted by the dynamical core. So aspects of the large scale circulation, stratospheric transport and dynamics, and then aspects of tropical dynamics and the hydrological cycle. Obviously, all of these things can be heavily impacted by the physics and tuning, but things like that Peter has looked at in more idealized settings, so noise over steep orography and things like that, will be examined. And so the idea is to have kind of 3 groups of people involved in this. There's going to be the DICOR task team, which will be the people that are doing the running and the setting up of the simulations and the analyzing of the simulations. And then there's going to be a DICOR assessment panel that will be mostly people that are external to NCAR, who will be considering all of the different aspects that need to be considered when choosing which dynamical core to use. So they will very much be interacting with the task team, who will be doing the analysis and receiving that information from them, but they will also be considering other factors like the inherent properties that Peter's already looked at, and kind of interactions with the stakeholders and computational efficiency and all of the other things that need to be considered. And then there's the stakeholders, which are the people who have actually developed these dynamical cores, and Peter's on for each of these because he has been responsible for getting each of these dynamical cores into CESM. And an important point is that the task team will very much be collaborating with the stakeholders when it comes to getting these up and running and tuning. And if there are obvious issues that come up, then the stakeholders can help to figure out exactly how to tune those issues if it's well known. So here's the timeline for how we expect this process to go, but obviously this could very much be subject to change because many things could come up that could delay the process. But at the moment, we still need to figure the configuration of the vertical grid that was talked about yesterday. And that's so far been run with spectral element, although the full vertical grid with the enhanced boundary layer and the high model top has not yet been run with spectral element. Peter is completing the integration of MPAS into CAM at the moment. And so the hope is that these 2 things will be finished sort of late March. And then we'll start setting up the initial tuning of the 3 dicores, and at the same time develop the diagnostics that we need to look at them. And this could take some time because we don't know what's going to come up. And so a tentative timeline for this is late August. And then once we have kind of suitably tuned and running versions of each of the dicores, we'll extend simulations out for the historical period in AMIT mode and do a first round of assessment. And then after that, so that would be late October probably, and then decide after that, do we want to do more simulations to check robustness of differences that we find, or are there any kind of glaring issues that might be tunable, and revisit that, and then possibly after doing that, run some more simulations to deal with either of those issues. And then we'll complete a first report on these IMIP simulations in proposed date of late January next year. And then, and all this time we'll be interacting with the other groups. And then based on whatever we find from these simulations, we'll decide on the next steps. And so, I mean, it's possible that one dicore could be ruled out at this stage, but probably unlikely. And then we would carry on with what we think is the most appropriate thing to look at next. Most likely we'll definitely need to couple to the ocean when that's ready. And we expect that this process will go on for about another year with a tentative end date of the end of next year to come up with an actual decision. So here's just a quick diagram of exactly how this is going to work in terms of who's all participating and what they're all considering. So the task team will be running the simulations and doing the analysis and interacting with the stakeholders when it comes to tuning and dealing with issues or any particular diagnostics that they think should be looked at. And the task team will be interacting with the assessment panel, and the assessment panel will be taking all the other kinds of information that they need to make an ultimate recommendation to the SSE, who will then make the decision. So that's all I have, so we can open it up for discussion now. Does anyone have any thoughts on the process or diagnostics or anything to do with this? All sounds fine.
Did you talk at all about the role of coupled simulations here?
Yeah, at the very end, I guess that would be the next phase, and will happen whenever mom is available and ready to be coupled. So yeah, I think the idea is that that would be starting sometime early next year.
I mean, this is Gökhan. Depending upon the progress, we can do some preliminary. I mean, mom is already doing some coupled simulations with the existing atmospheric model. But as the maybe candidates become available towards the end of the year or in the fall, we can do certainly some MOM6 coupled experiments.
Maybe I have a question on changing, we talked about changing the codes and having different forcings. So we'll, in our session, we'll talk about new aerosol scheme MEM5, actually for model aerosol model. Those change, also bug fixes change somewhat the simulation. And so it's good to know a deadline kind of when this all has to be in, so we can work accordingly and plan for it.
Yeah, well, I guess the according to the current timeline, it would be sort of April when we'd be starting. Yeah, so by then it's probably the time frame.
Right, which is actually very little time.
Yeah, I guess if there's critical things, then maybe we can factor that into the timeline. I don't know what other people think about that.
The physics group also needs to maybe discuss what physics version we should use. There are obviously some changes going in now to get the new boundary layer resolution running. But at some point, we need to just decide on a stable physics configuration. So that's why we wrote CAM6 plus in the slides.
So I have a question, and you'll have to excuse my ignorance because I'm kind of jumping between two meetings at the same time. But I'm curious if I saw that there was obviously a little bit of what's going on with the vertical resolution, and that's helped to inform some of the setup for the comparison. But I'm curious about what role the capabilities of the die cores have, such as variable resolution or efficiency at really high resolution, in terms of thinking of the science problems that this model will be developed to tackle. If that really is if that's gonna play a role, or if it's really kind of looking at kind of the work, I know we don't want to use this term anymore, but like the workhorse, kind of like the official version with the default core. Is that really the sole focus for the analysis of which die core will be chosen?
Do you want to answer, Peter?
That's a really good question. If we could, we would do everything. But we just view it as the highest priority for CESM to kind of have a 1 degree climate change configuration. But obviously that's something that will go into the decision process. What about the higher resolution and the capabilities of the different die cores to meet the needs of, for example, variable resolution and very high resolution applications. And I'd also like to say it's not unlikely we're going to have different die cores for different applications, such as we have now, where we have finite volume for 1 degree spectral elements for quarter degree and mesh refinement applications. As we're kind of trying to keep this manageable to just start with the 1 degree, because I think there's broad agreement that we do need a good 1 degree model for a lot of our users. But I agree, we have a lot of frontier applications at higher resolutions that needs to be taken into account. So that's my vague answer to your question.
Well, yeah, so I would just maybe add that, I understand that you can't do everything, but this kind of then the piggyback on the conversation from yesterday is that I think, allowing users to have tools so that if they want to run a different die core that's not the official die core, tools to evaluate how well the simulated climate compares in their configuration to the official, to have some measure of if it's scientific, of course it'll be maybe qualitative of whether it's, scientifically validated enough for the purposes of the science. But I think this is a really important thing that from the NSF perspective, right? If you have PIs that are making proposals or submitting proposals to do science with the model, it has to be a way in which we can verify that the setup that we're using, even though it's not the default version, is at least reliable for the task at hand.
And also in terms of, none of us mentioned this, but with the CSM 2.2 release, we introduced a new category of release called developmental release. So that means, all the files are there to run the simulation. We have done some science validation, but it's not validated to the level of a CMIP model. So once we've gone through this tuning exercise, then everybody will have a pretty well-tuned baseline for these different dynamical cores. And but yeah, we need a very flexible setup. That is where we're moving towards.
And Kevin, just to sort of reiterate what you said, we are also going towards providing what I'm calling personally recipes for configuration setups that people can use. So one example that we are actually doing right now is for the ultra high resolution, cloud resolving version of CAM, for example. But we can, the idea is to expand that. And then if people want to use MPAS atmospheric dynamical core for, I don't know, weather related applications, there will be a recipe. If people want to use a C-die core for right now we have the Greenland version running, for example, and I know that Andrew is working on the Arctic versions of that. So those recipes can be provided and they'll be included within the model, but not necessarily perhaps as fully supported releases, but they can be developmental release or a functional release. So the idea is to provide all those recipes to the extent possible.
I guess really, sorry.
Kevin. Go ahead, Isla.
Just related to this point, I think there was a question in the chat about forcings and whether, I guess basically whether all the comp sets will be available for.
Well, so Julio, did you want to speak to that?
No, I'm waiting. I'm going after you. If
okay. So I think it's a great point, Kevin. I think one of the sort of been hinted at when we talked about yesterday, one of the principles of the CEMA is that it should enable all this to be a lot easier to do. We are going to support multiple dynamical cores within the framework, and they should be configurable, as Gökhan said, and we will have recipes or comp sets that allow that configuration. So I think that is all going forward. I think what you said is actually very interesting, and one of the things that CEMA, I think, is trying to focus on is improving the workflow. And so to make it easier to do what you want, which is actually to customize things. And there is a tension between over customization and just having set things that actually work. But it is an interesting concept to develop tools or evaluation strategies where we define what is scientifically acceptable. But again, the problem with that is what's scientifically acceptable for us may not be scientifically acceptable for your problem, and vice versa. So I think if you start going into the developmental space, as Julio was saying with developmental versions, you are going to have to do more work on your own. And then I think the last thing to note that Isla was commenting about on the forcings is something I mentioned yesterday, that one of the things we're doing is we're developing an inline regridding system, inline interpolation system, so that you don't need to actually do a lot of work with the forcings for CESM if you're doing different configurations with different grids. If you're doing a customized, once you define a regionally refined grid, you won't actually have to go generate all the forcing files for that. The model will be able to use the existing forcing files and know what the grid is. So I think that will improve the utility for a lot of these specialized problems as well. And if there's other things we're missing like that, I mean, we've identified that as a key issue in usability. But Kevin, if you and others have key hangups where you try to reconfigure the model and get hung up on something, let us know, because we need to try to fix that. And that's something we can actually work on. So if there's other things other than, because we know if you have to reinterpolate forcings or nudging files, it's a huge pain point. But if there's other things we're missing, if there are other pain points you find, let us know, please.
Can I find I can't have the raise a hand facility. Can I just talk? Sorry. So one thing that I've mentioned in the past, and maybe is a bit controversial, but that could also be considered maybe by the development team and also by the stakeholders, is to make the code readable and well documented. It's something that people like me and others in the WACCM community appreciate very much. And it is, I would suggest it should be considered as part of the model quality when the code actually matches what is doing what it is said to be doing. So that would be maybe one point to consider, perhaps. Also, in the evaluation, I have found it useful in the past to check the energy transports within the atmospheric model itself. When you're running with constrained SSTs, then the climatologies tend to look quite similar, but you can find big differences in the enthalpy transports, actually. And that could be maybe part of the evaluation also before going to the coupling stage, when the ocean model will be sensitive to those transports and might have to be tuned a lot or not very much, depending on how different they are.
Thomas, are you referring to improve energy budget by increasing the complexity of water species we track? Or you're referring to evaluating the current model with certain enthalpy metrics?
Yes, so I was thinking of both, but I think I tuned my comment back to the second option, because I know that the first one can be a bag of worms. It is interesting actually to consider how you compare energy conservation in the three different dynamical cores. There probably, for local energy conservation, you probably have to use different recipes to be consistent with the die-core formulation.
Yeah, so that's what we have under the intrinsic properties, is to look at the energy budget. And that's actually what we're looking into with MPAS now, because now we have a different vertical coordinate. So the assumptions made in the energy formula on the physics side are not applicable when you use a different vertical coordinate. So we are running into these kinds of consistency issues. And another thing, yes, I wanted to bring it up yesterday in our, oh, go ahead, Thomas.
Sorry, I was just saying that when you actually change the coupling fields, when you take account of additional tracers in the couplings themselves between land and atmosphere, ice and atmosphere, then you probably need to take that into account for the evaluation of energy conservation in the atmosphere itself as well.
Yeah, so we had a meeting just last week, because the coupling with MOM6, Gökhan can correct me if I'm wrong, but I believe MOM6 is a constant volume model, not a constant temperature model, if that's the right formulation.
Mass conserving model.
Yes, that will force us to have a look, reformulate possibly the interaction between the model components, which again interacts with the energy of the whole system. And the other point I wanted to bring up yesterday in the physics discussion is we may think about for CAM-7 is to more accurately handle the energy budget on the physics side. In particular, we have this constant pressure assumption on the physics side that can lead to rather large local energy errors that we're currently just fixing with the energy fixer. And doing that more rigorously, as you know, is quite complicated, but I think that should be put on the list of possible advancements of CAM-7. But it involves many parameterizations. It's not an easy fix.
I think this brings up this general problem that we're moving slowly but surely towards non-hydrostatic dicores, potentially with a z-coordinate or height base coordinate in the vertical, and that brings up these questions. So yeah, I think there are all these design decisions, also the speed, the performance should be looked at, even maybe portability to GPUs. That's probably far-fetched for CAM-7, but I think this becomes a topic in the future.
Well, actually, Christiana, that's an important part. GPU friendliness of the dynamical core would likely be a consideration, as NCAR's next computer is 20% GPU based. It doesn't mean that the entire dynamical core should be running on GPUs. In fact, we are in talks with CESL on heterogeneous applications. And certain part of the die-core can be running on GPUs, while certain part is running on CPUs.
So I just want to mention that Leo has a point on high resolution, might be related to this.
Yeah, thanks, Julio. And actually, Gökhan can probably comment a little bit more. I don't want to stray too much from the die-core, but responding to Kevin, there are, in addition to kind of the recipes approach that Gökhan was mentioning that would be made available to the community for high-core, some allied projects. So one of them is IHESP, and these are series of high-resolution runs that have been done with CESM. I think it's on the Sunray computer in China. It's the 4th most powerful in the world. So right now, I believe those are available already, coupled with 1/4 degree atmosphere, 10th degree ocean. The thing is, you don't get to design the runs, but there could be available there things that would be useful for some of the things Kevin would like to do. And that data is going to be or is available. Gökhan can comment on that.
Yeah, it's mostly available, but the full set,
going forward with the new die-core from CSM. Gökhan, do you want to say anything?
Yeah, I mean, we have a 1/4 degree atmospheric model, CAM-SE die-core, CSM version 1.3, coupled to 1/10 of a degree ocean. We have 650-year pre-industrial control. We will have 3 ensemble members of the 1850 to 2100 period. We have all the high-res MIP simulations that are already available. And we have also forced ocean ice coupled simulation with JRA 55 forcing. Not all of them, but quite a bit of the data sets are already available from the TAMU website. And all the remaining data sets will be, in fact, we just received the last shipment. They are being transferred from China using FedEx tapes. That's the only way we can get them. So they should be downloaded and checked for security purposes, and hopefully they'll be available probably in April or early May timeframe to everybody. The full data sets, they are partially available right now.
Yeah, and the other possibility, which is, I would describe it as an allied project, it's got about a 5-year timescale, but Cyber Infrastructure Initiative at NSF has funded something called Earthworks. This is a project that Dave Randall is leading at CSU. It's going to be, I think, about a 5-kilometer atmosphere, 5-kilometer ocean, fully coupled Earth system model. And it's different from CSM. Their plan is to use MPAS-O for the ocean die-core, and I think they've already settled on MPAS-A for the atmosphere. But they are planning to build it in the CEMA architecture. So although may not be CESM, as if it develops scientifically in a productive way, the fact that it will use CIMA could make it easy for members of the CSM community to use it going forward. So, that's again not CSM, but it's closely aligned within NSF. And as we go to having a CSM supported by CIMA, there becomes a common framework. Andrew was already alluding to this. It opens up some possibilities for things we may not be able to do ourselves in CSM. And Gokhan may want to follow up on that one, or Andrew also on the CIMA being a common thread here for some of these.
Yeah, I think that's correct. I agree with that.
I have a question for Ayla, because you mentioned yesterday that the choice of the boundary layer resolution, the vertical resolution, would be imminent. And I wonder how realistic this is. You talked about a few weeks.
Yeah, well, yeah, I guess end of March is what was on the time frame. It depends, I guess, how easy it is to tune. I mean, it looks fairly reasonable in many respects at the moment. And I guess we still have the issue of exactly what we do at the model top, but I think we've tried both options that have been suggested. So I don't know, Julio wants to say something now.
No, I was just going to say that one hang up on the increased boundary layer resolution front is Jean McFarlane, where we probably want to recode Jean McFarlane, which Rich is actually already working on, to do something different in the bottom, in the bottom layers to decide its cloud-based properties. But I don't think that's, well, I'm speaking for Rich, but I don't think that's a tremendously daunting thing.
Do you think
that has to be done before we finalize the PBL?
Yeah, Julio, in my experience, that's not the problem at all. As soon as you remove that dependency on the lowest layer, then the model behaves actually. So it's not a problem.
Okay.
One thing that I was going to, I didn't attend all of the AMWG meetings, but I thought that there was still an unresolved issue with the moisture related stuff, right? At high vertical resolution.
Oh yeah, that's another ZM issue.
And is it easily fixable, or is it?
That's less. Well, again, I'm throwing Rich under the bus here, but again, Rich is trying to develop a more physically consistent way of deciding when Jan McFarlane actually can be intercepted by stably stratified regions in the atmosphere. Right now, apparently, that's done in a kind of vertical resolution. It's done in a way that's not physically consistent. I think that is, the gradients are not looked at with respect to height. It's just changes over levels, etc.
It's sensitive to level number and not DP, which of course, as soon as you increase vertical resolution, you're in trouble. Yeah.
Right.
And so the timeline. Oops, go ahead.
Oh, I was maybe just going to ask the same thing. Is this like a few weeks kind of a thing,
Yeah.
or is it?
Yeah.
Okay.
Yeah, I've done this in the past and it's worked out quite well. So I just need to reconfig for this setup.
And that upper tropospheric issue is really more, I'm going to get in trouble. It's more of a chemistry concern. I mean, I don't know, have we figured out whether it has big impacts on high level clouds? Well, it's something for us to look into.
Is this a tape recorder, the dry tape recorder issue?
Yeah.
I mean, we had looked at, I think Brian had looked at clouds in all of our vertical resolution tests, and there wasn't anything dramatic.
Mm-hmm.
And that issue was there at that point. So.
Okay.
Yeah, nothing that looked super terrible. I think we need to take a closer look eventually, but I'm not overly concerned about it yet.
I mean, it is interesting that I vaguely showed it in my talk yesterday that Club is doing a lot above the deep convection. And so how that's going to respond to vertical resolution changes up there, it's not clear to me.
Yeah, I just want to caution, I think it's an aggressive timeline to think we are done by end of March. I see some potential hiccups.
Yeah.
Well, I'll just throw out that talk later today by Levi Silvers is going to look at some of the differences in CAM-5 and CAM-6 and really idealized RCE simulations in which clouds do different things between them. So it's just a potential avenue to explore some of the things in a more controlled setting, potentially.
The RCE framework.
Yeah, and with and the official RCE MIP comp set, which is part of CESM too now.
Right.
Also, for those of you who want to work closely with our group, please let us know. So if you want to call into our meetings, I'm referring to the DICOR task team. So please let us know if you want to contribute or be part of it.
And just to reiterate that point, I mean, we want the whole process as transparent as possible. And throughout this process, the idea is essentially to communicate, just like in this kind of venue and all that stuff, or the summer or email exchanges. So that's the idea. So
Adam has his hand raised.
Yeah, I have a separate question. So what I've been finding is that moving away from the latitude longitude grid to these quasi-uniform grids seems to degrade some processes in polar regions that benefited from the convergence of the meridians. And Peter had showed one example of that with the his tracer mass conservation experiments. And so I accept, we're going to be moving away to a quasi-uniform grid resolution, but very small changes in grid spacing can have a noticeable impact on features that are kind of approaching the resolve limits, such as the Greenland ice sheet, which might only be 10 or 20 grid cells across. And so one thing that I am just a little concerned about is that the FV cubed, MPass, and CAM-SE CSLAM 1 degree configurations all have different degrees of freedom. And so FV cubed has 55,000 grid columns. CAM-SE at NE30 has 48,000 grid columns. And I think to favor one die-core over the other because it tends to have more grid columns and resolve some of these features better is not really an apples to apples comparison. And so I just wanted to throw that out about potentially trying to normalize the grids that we're comparing to so they have the same approximate grid spacing.
So you'd advocate having the same number of columns in the tests?
Yeah.
Yeah, it's definitely not apples to apples. What we have done is use the nominally 1 degree configuration given to us by the developers. So that's how we have proceeded until now. But you are right, MPass is even less. I think it's 40-something thousand. So there's 15,000 plus columns difference between FV3 and MPass, for example.
That's almost 30%.
But does it make sense to use a grid that is not one that's preferred by the developers of the DICOR, or does it not matter?
I think it's a conversation worth having with the developers. It's funny because the FV cubed has the same number of grid columns as the FV grid at 1 degree. So there was a conscious effort there to not reduce the number of degrees of freedom going from FV lat long to FV cubed. When we were deciding that NE30 was going to be the standard 1 degree for CAM-SE, we didn't have any guidance. There was no guidance to try to pin it to the same degrees of freedom as the FV lat long. And I'm just suggesting that maybe they should be all normalized to have very similar grids. And I would personally think it would be worth asking the developers what they would think about doing that, because the process of implementing a new grid isn't that difficult to do in the grand scheme of things.
But you could also argue that you should compare equal cost rather than equal grades, potentially, right? So it's not obviously a high order scheme will be more costly, but in principle you should need a smaller number of grade points, while if you use first order upwind, then you can use huge number of grade points and for the same cost. So maybe I'm just saying you could argue also in another way. It isn't necessarily. Also, the degrees of freedom of VFV are actually reduced in the polar regions because from 63 degrees poleward, you start heavy filtering. So you are throwing away degrees of freedom there as well.
Oh, yeah.
So it's not entirely obvious, what the degrees of freedom are in the code. It's not necessarily the number of columns you're using. Well, the physics is, of course, but the DICOR isn't.
Fair point.
So it seems that there's importance to have some additional information of not only what the grid points are, right, because that is important for potentially with what the physics costs of the model are, but in terms of what is the computational efficiency, but also what is the effective resolution, right? Because that can be different for different DICORs, and how you define that is probably not necessarily completely clear, but I think that that is something that needs to go in, because even if you have the same number of grid points, but your effective resolution is slightly higher, you can actually get a very different simulated climate or better climate potentially. But that comes at the cost of a more expensive DICOR potentially, and so. There has to be a suite of metrics, which I think Ayla did mention a little bit in her
yeah, talk. And Kevin raises a great point. It's actually not just the number of grid points, it's also the order of accuracy. For example, SE has a higher order than the others, which makes up for some missing grid points. I also would like to remind everybody we only have a few minutes left. There's a CGD seminar at 11, so I suggest we maybe take 3 more minutes or so to finish up this discussion. And I think Elizabeth also wants to communicate, maybe via the chat, or not certain whether she wants to show a slide. She wants also to provide the information about the CGD seminars. Everybody's welcome to dial in. That starts at 11 Mountain Time, so in 13 minutes. So just let us maybe use 2 or 3 more minutes and wrap up.
The one thing to keep in mind is also that the modeling groups might have spent a lot of time creating a really good 1 degree, whatever their 1 degree resolution is. So I totally see Adam's point that it's not apples to apples. And there's a lot of other stuff that's not apples to apples. But if we start changing this, that would definitely add to the timeline. But it is something we should make people aware of course, when we look at the results.
It's even difficult to know what FE3 does. There is very little documentation, as some of you know, about these filtering settings, for example. So that would be a good effort for this team to also provide a clear view of what the right choices are.
I'll just add that I think it'd be pretty straightforward to look at I think part of the diagnostics should be looking at the KE spectrum together, and that'll give us an indication of effective resolution differences. But in the chat, and Peter is sort of seconding with Thomas that he thinks the best metric, given the choices, is throughput. He says, put another way, a finer resolution may result in better skill, but will be penalized for computational efficiency. And so another diagnostic, I think we should compare the throughput at low core hours. I'm sorry, low number of nodes, just to see how big the spread is.
Yeah, so we are looking at stuff like that.
Yeah.
So Peter Caldwell just raised another point. Do you want to speak up, Peter?
Yeah, it seems like PhysGrid is working really well for E3SM. So the idea of using a coarser grid for your physics than for your dynamics. And so I was expecting that this would end up being the default in CAM-7. And it seems like that choice would probably project onto at least the die-core inner comparison in terms of efficiency and climate skill. Has anyone talked about that? Is there any plans?
We're running the baseline simulations with CESM where we're using a physics grid, but we're currently keeping it at the 1 degree resolution. It'd be very interesting to run with the 2x2 physics grid because physics is half the cost, but then again, we're even less apples to apples with the other die cores. But I think it's something that needs to be highlighted during this assessment that, for example, SE has that functionality. And similarly with the other die cores, there could be things we could highlight. So for example, one interesting thing is that MPAS usually runs with a lot rougher topography than what we usually use for climate. So that could be one thing we could highlight, that die core can handle rougher topography. So I think we need to think about all these different extra attributes that the different die cores are, but we initially here, we just want to keep things manageable. But the 2x2 physics grid, if we were to use spectral elements, like that would be an interesting candidate for paleoclimate since throughput is an issue.
Right. Maybe just have a page somewhere and just write down all of these things so we don't forget them, and then forget them since you can just look at the page.
Yeah, that's a good idea.
So this has been a very insightful discussion. Thanks a lot for all the contributions. And again, Elizabeth posted, when you look at the chat, she posted the information about the seminar starting in just 8 minutes. I suggest that everybody has a little bit of time for a break now and that we close this session. Julio, when are we starting again? Can you remind me?
Yes, we're starting again at 1. We have two sort of sessions from 1 to 3 on clouds and aerosol climate effects. So that starts at 1 Boulder time. So yeah, I think people should take a break and attend the seminar if they'd like to.
So this stream will stay open for a few more minutes until 1. So if somebody wants to stick around, feel free.
Yeah, according to Elizabeth, the stream is going to stay open for
even 1 p.m. Mountain time.
Until 1. Yeah.
Oh yes,
it's going to stay open, I guess, perpetually. Yeah. Well, for the duration of the meeting, anyway.
Yes, it stays open just so it doesn't disrupt the YouTube stream.
Right.
Mm-hmm.
All right.
Ready?
Yeah, thanks.
The number of participants is falling really fast right now.
Yes. It's lunchtime here.
Yeah, that's true.
1 p.m.
It was good though. I saw a high of 67 people this morning.
Yeah.
It was like 130 yesterday. It wasn't up for my talk, but I think just before.
This is die-cores, Rich.
Yeah, that's right. Yeah, I'm surprised it's not single digits, but hey.
Yeah.
I do have to say though, early on in our meeting, it was some people who thought they were coming to the paleo meeting.
Uh-huh.
And then they hopped off to go to paleo. So there was a little bit of a crossed wires with Zoom links.
Okay.
Well, we'll still count them.
Well, yeah.
Yeah, Rich, you need to try the new topo changes that Mark put in.
Yeah, someone was mentioning. Yeah, I looked. It'd be good to. You have FV3 simulations that just aim it, don't you? That you and John put together.
Yeah.
I'd like to look at that too. Yeah. Okay.
Yeah, well, we'll have a new bunch pretty soon.
Yeah.
It's just a while ago we did aim it with FV3.
Yeah.
So Peter, how can I get access to your newest SE updates?
I have it in a GitHub repo. That's That's the one I'm going to do my pull request to CESM with. So if you want to use that, you can use that.
Can you point me to it?
And yeah, and another detail is we're also able to not have increased divergence damping. So Cecile is doing a run right now, and it looks like it ran 2 years stably with the 80-kilometer top.
Yeah, and I stopped it at 2 years.
Yeah. But yeah, the mods for topography is really night and day change in terms of the vertical velocity fields. And then I hope we're done changing stuff.
Did you change the pressure gradient force computation?
Yeah, well, before CSF22, we switched to an external pressure formulation. And then Mark found that if you subtract a reference profile to that as well, that helps the noise issue. And we already had the reference profiles for temperature and pressure diffusion. But one extra mod that we put in was to do temperature diffusion on approximate Z surfaces instead of model surfaces, like what is done in the spectral transform core. That also made a difference, in particular in Hell Suarez, if I remember correctly. So it's pretty little code and minor tweaks, but it really helps. And then go ahead.
Once we tried a block mountain and SE blew up on us, the others actually tolerated that, but that was too steep. Of course, it's super steep.
I think it should do better with these new fixes. But high order methods don't like grid scale forcing. So yeah, and then regarding the sponge, it's really funny that the del 2, like just increasing the coefficients, don't really do that much, whereas the del 4 really hammers out the small scale. So when you're running with the 140 kilometer top, we've had tremendous stability issues, and del 4 seemed to be the simplest and easiest way to damp out the small scale gravity waves. That's what I saw. I ran your moist Hell Suarez test with spectral element out of the box, and there was a huge amount of noise. And then I added increased del 4 in the top 2 layers, and then that noise went away. So I'd be curious to see if that helps.
Even with 30 levels, or are you?
That was just 30 levels. Actually, I didn't have the issue with the higher top. So there's some wild gravity waves bouncing around in the low top model that the del 2 did not really take care of. Mark is on the line if he has played around with that.
No, I want that fixed though, or I want to try that.
So
I'll warn you, Peter, I got another topo improvement in the works.
The chemistry folks might get upset because they've had to bear with a lot of changes. But as long as it has a couple of lines, then. But Cecile has just run a historical simulation with the topo changes that we're going to look at with the 80 kilometer top.
So I had a question. I didn't ask it during the discussion, but is there any impact or is there any importance to the thermodynamic variables that are used in the dicores? I mean, I just, some use T, some use theta, some use virtual, etc.
Yeah, you got to be really careful in the coupling.
Yeah.
So that first showed up in the baroclinic wave, that the surface pressure, like John saw that the surface pressure was, I don't remember how much, 3 hectopascal off with MPAS. And that was simply due to how we compute surface pressure, because that's a diagnostic at MPAS. You got to be really careful how you compute it.
Okay.
So after a couple of pages of math, I figured out how to do that. And right now I have the issue with the energy fixer, because I can add the temperature increments from physics. You can easily convert them from constant pressure to constant Z assumption, which is assumed in MPAS. So I got that part figured out to round off. But the adjustment to water vapor is very different if you do that in Z coordinates or pressure coordinates, because first of all, it's an inherently inconsistent thing to do in the first place, but we are doing it. But the tendency computing that in Z coordinate and pressure coordinates are way different.
You're talking about real moist. You're talking about moist pressure coordinates, not dry pressure coordinates. Or
yes, at the very end of physics, we have assumed that pressure stays constant.
Right.
But when vapor is either converted to a different form of water, or falls out of the atmosphere, we have to take that into account energetically, and we're just doing a global fixer.
Yeah.
And computing that with different assumptions of the vertical coordinate is very different. So if we don't think about this, we end up having the energy fixer fixing that inconsistency. So I'm currently trying to figure out what to do.
Is that fix actually done in Kessler when you have Kessler configurations?
No. You can turn it on easily if you want to, but I think it's energetically inconsistent because the physics is not energy conserving. So right now, it's only when you run adiabatic.
I think I referred to the pressure the pressure fixes. After.
That's not done. To my recollection, that's not done. But I have to double check, but I don't think so.
Is this issue you're talking about is more a matter of just careful coupling, or will one actually be, since the physics is all temperature based, is it better to have temperature as a prognostic variable?
No, the conversion is pretty straightforward, except when you compute energy, because it uses temperature. So I had to be very careful how you convert theta to temperature. And that part I've got figured out. If you do that carefully,
right, I think
that can be consistent.
It's tricky and you have to do it carefully, but once it's done right in both cases, there wouldn't be much difference.
Yeah, it's the DME adjust, the pressure adjustment, that one. They're very inconsistent right now. I'm trying to figure out what's going on.
You do change the conservation properties of the dicore if you go with temperature versus potential temperature. So
I think from that point of view, there's a correct choice, right? There's the structure preserving. The one that comes from the Hamiltonian will be tied to the pressure gradient.
But there remains a fundamental inconsistency in the physics, though, that I think Peter was mentioning before. So the energy conservation at the moment can only be achieved column by column and not really locally. Because the physics is assuming a constant latent heat of evaporation. And physically, that implies the same heat capacity for liquid water and for ice, which is an assumption that is broken elsewhere. So essentially, the physics is internally inconsistent. And therefore, energy conservation is violated systematically.
Is that error? How's that error compared to the constant pressure approximations? I would guess is even larger.
No, it's not. No, it's an issue of taking account of the temperature dependence of the latent heat of condensation.
Yes, if you want to use, that's why CAM physics is now consistently inconsistent now, because it uses the dry heat capacity for water vapor. But if you use the correct heat capacity of water vapor, then you need to have the latent heats depend on temperature.
Yeah, and that is still fine, but then you are obliged to have the same heat capacity for water vapor and for liquid water. And that is the big falling block, the stumbling block, because they're obviously quite different, and any other component in the model will not make that assumption, including clouds. So it is internally inconsistent, and there is no way out. I've tried in DME adjust, as you know, Peter, and I had done something in order to have local column conservation in the local column. consistent with the exchanges at the surface. But there is no way to fix that within the column until the physics is actually doing its job, which would be to do the thermodynamics as in the real world.
And it's not doing its job for several reasons. You're saying that it doesn't have temperature dependent latent heat, and it also doesn't, well, currently it does not allow the pressure to change when molecules leave the atmosphere.
Yeah. So
I think we need to follow the energy.
Things, yeah, exactly. These three things are, or rather four things, if you'd like, are all mutually dependent. So the enthalpy associated with mass fluxes, the temperature dependence of latent heating, the heat capacity difference between water vapor and liquid water, and the pressure adjustment, they are all interdependent. So you cannot have, the energy conservation requires all these three things to be, four things to be consistent with one another. Yeah, so
you also need to follow the energy of the falling precipitation. No, and that needs to reach the surface and then exchange.
The kinetic energy of the falling precipitation, or
well, you can include that if you want to, but I'm just saying if 1 kilogram of water is removed at whatever 200 meters, we have to follow that energy properly, you know, and follow the droplet and make sure the exchanges are energy consistent.
Yes, so the potential energy of precipitation is quite a lot, as we know here in Norway. I'm heating my house with it, and that eventually gets into thermal heating, frictional heating, that is sapping the kinetic energy of the falling droplet.
Yeah.
So yes, you do have to take account of the kinetic energy.
Yeah. There has been, last week we were talking, like in a couple CSM meeting, we were talking about taking into account the water hitting the surface with a different temperature than the surface. So that's on the radar now in CESM.
Yeah.
I have something there if you want to have a look. But the problem is I'm not happy with any of this because it's always a hack. I mean, you can do things, but they're a bit better, but not right still.
But I think we're at the point where we can do all four things that you've mentioned correctly in the physics for the next version of the model. I think we should.
Yes. Yeah, I think it's desirable now.
Yeah.
I'm unclear how much we need to go into the individual parameterizations. Like if we can just assume that they're right point-wise and do these energy exchanges outside or not, because if we have to go into,
for example, also is making those assumptions, so club would need to be changed.
Yeah, I think we should. Go ahead, Thomas. I'm sorry.
Yeah, well, same for the convection. You are working on that, so that's going to be fixed. I expect, and that will be great. But yeah, the cloud physics is trying to take into account proper water, ice, vapor phases, so that should be fine. At the moment, it's using some tricks in order to interact with club and with deep convection. So in order to make it look like it's conserving energy. So yes, the physics needs to be.
Yeah.
Have you put the water loading into CAM already?
Yeah.
Does that go into the pressure in the into the physics?
No, but I was planning on. I don't think that's hard, just to add it to pressure.
No, it doesn't. It doesn't.
So just to put cloud, ice, and liquid and rain, snow into it. But I tried to run at 1/4 degree and look at how big the pressure loading was, and we couldn't even see it. But using the correct heat capacity for water vapor did make a big difference. But then the dicore is inconsistent with the physics, so that leads to like 0.5 watt per meter square we're fixing.
Yeah, I think the pressure loading from condensates will become more important, obviously, as updrafts can keep the hydrometeors aloft for. I mean, right now, I guess our profiles of hydrometeor density are small at 1/4 degree.
Do you know if in the DME adjust the change in pressure is it from precip leaving the model, or is it from transfer just into transported liquid and ice out of vapor?
Well, it's both, no, but I.
Well, it goes so the vapor is offloaded, and the liquid is assumed to be massless.
Yeah, so if there's a phase change from water vapor to liquid, that goes into DME adjust. But I think if we included those in the pressure, then it wouldn't have an effect.
No, that's right.
So that'll be
until it reaches the surface.
That'll be a first test.
They'll be adjusting the water that left the model.
Yeah.
Or enter, of course.
Yeah, I think those terms are probably a lot bigger than the conversion from water vapor to liquid and ice, I would guess.
Yes.
So the enthalpy flux of precip is the dominant term that is trying to fix.
Yeah.
Yeah. The local mass change of water vapor.
The specific enthalpy of the water.
Yeah. That was carried out of the model.
Or
but DME adjust is putting it back into the temperature.
Yeah, converting mass into heating.
Converting mass that left the atmosphere into heating.
Yeah, it's not even there.
I guess when I was working on my topography studies, and that's my question for Peter, FE3 had a +11 hectopascal pressure signature. So the other models dropped way further. I actually wonder whether there is a DME adjust in all Kessler configurations, and whether it is called after we remove the moisture in Kessler. That would
let me check.
Because I think that could explain why FE3 looks so different.
Yeah, as I remember, in front of the DME adjust call, there is a Kessler. The model does ask whether Kessler is active, and then we do use DME adjust.
Right, but is it also for FE3? I think that's the newest version.
Oh, I don't think. Oh, I wouldn't think that is dependent on the dichord.
Oh, maybe that's in the physics end. Okay,
well,
but is there a yeah? Okay, I need to maybe do this offline with Peter just to investigate.
Looking right now. The thing is that there's a phys package for simpler physics and then one for the full. So, yeah. Oh, you're right. There is if moist physics, and if you're using finite volume or FE3. Oh, that was just set wet to dry. Just a sec. See if there's an actual DME adjust. Yes, there's a. No, that's just for. Yes, there is.
Okay.
You're right. There is a DME adjust, but there's no energy fixer call.
Yeah. Okay, but there is a pressure fixer.
Correct. Yeah. Okay. And it's called. It has to be called for moist vertical coordinates. It's called for FE and FE3, and then in SE it happens implicitly.
Okay.
As I think these thermodynamic issues are those errors are much larger than probably than non-hydrostatic effects, at least at this point in the game.
Well,
speaking of non-hydrostatic, Thomas,
sorry,
go ahead. No, go ahead, Thomas.
No, I was just saying that I would like to be, involved in this evaluation of dichor, since you invited And yeah, we have an interest here in trying to figure out what we shall do.
Do you wanna be on the task team because we're gonna meet quite frequently, so we can put you on the list. But that will be like maybe bi-weekly.
Every 2 weeks.
Yeah.
Or twice a week.
Every 2 weeks.
Every 2 weeks.
Every 2 weeks is okay.
Yeah, and we're meeting currently. If we're taking a slot that we're using right now for a lot of die-core stuff, it'll be 9 a.m. Boulder time, so 5 p.m. your time on Fridays.
Yeah, that's perfect.
So if you want to do a happy hour with die-cores, you're most welcome. It'll be good to get your input.
Okay, great.
Peter, how much will it take to turn the FE3 into a non-hydrostatic die-core? Is this just a switch?
Well, the way that's done in FE3 is it's if-defs. So the actual non-hydrostatic code is not compiled. So turning it on technically is not a problem, but we haven't gone through. We need to reevaluate if the physics dynamics coupling is correct. And also, non-hydrostatic with FE3 takes a very different path in terms of choices of diffusion operators and so on. So it invokes a lot of code we haven't tested yet, but it should technically run, but we haven't had the bandwidth to get it going. Like all hands on deck on MPAS right now. But John is pulling in the new version of FE3 to make sure we have the latest and greatest.
Good. Oh, perfect. From GFDL.
And we haven't officially contacted GFDL about this die-core comparison, so we need to officially contact Lucas and Ram.
What's John's timeline on that?
Timeline for
the incorporation of the newest GFDL version?
I've got a sandbox with it, and it requires the latest version of FMS. So it's, Mom is also using that. There's some other things that are, complicating our getting it in, but hopefully within the next month we can get that.
Okay, so soon. Great.
Yeah. So that's a big challenge with our timeline, is these known unknowns that keep popping up. But I'm pretty confident we'll get FE3 running pretty fast. We got it running really fast in AMIP without any major issues, other than tuning on the physics side. And MPAS right now has stability issues, so we're fiddling with sponge layers and so on. And I'm trying to figure out this energy thing or issue. Which keeps haunting us. So Marcus, are you guys officially running 2x2 physics grid in the main branch?
Yeah, it'll be in the V2, all the, what we call the V2 models, all PG2. No, we're very, very happy with that. We needed both. You need that to get the factor of 2 in the physics, and you need semi-Lagrangian tracers to get a factor of 2 in the die-core, and only the two together do you really see a factor of 2 in the atmosphere.
Yeah, we're only seeing 20% improvement with PG2.
And the scientific results are comparable?
Yeah, we really thought PG1 should work, and it doesn't. It has a degradation. But PG2 looks quite good.
At 1 degree?
Yep, 1 degree.
So 1 degree dynamics and 1.5 degree physics?
Yes. That's a point of contention, because the physics people, since they only see the PG2 grid, they want to now call the model 1.5 degree.
Yeah.
Like, no, it's a 1 degree model.
Yeah.
Some downscaling of the output.
Yeah. Do you have a paper coming out on AMIP comparison with PG3 and 2?
We have a a comparison, including spectra. Walter Hahn is leading that.
Okay.
But I think the official AMIP or CMIP, probably like paper, will just be PG2. It won't have a comparison.
Okay. Because Adam was really close to having a paper ready, but he got distracted. Got a new job too. But in terms of the mean climate, we didn't see any major differences.
Yeah. We've done a lot of work with the DCMIP test cases, Moist Bear Clinic.
Mm-hmm.
That's quite sensitive if you run it out, like 30 days.
Mm.
That was actually quite useful. That shows differences at PG1 and almost no differences at PG2. So this is just like a coffee break, but live streamed on YouTube. But
it's live streamed on YouTube.
But I just since it's free form, what's the? I'm curious to know if we can switch the top of model sponge layer. If we should just, you're saying just use the regular hyperviscosity and just crank it up as you get to the top of the model, and drop a separate sponge layer, Laplacian based, or do you do both?
I haven't tried to drop the Laplacian. So given the discussion from yesterday, I put it really low where we start ramping up L4 because to do it conservatively. So I haven't done the sensitivity test of how high I can pull it up. So I'm just using this tangent hyperbolic profile, and it's centered around level 10 right now, but in low top cam it's just level 3, I think. But I need to do some more runs to figure out what is stable. But I just couldn't get the model to be stable with WACCM with just Laplacian.
Are we talking about a factor of 10 or 100, or what's the increase?
So all my scalings are based, so at 1 degree, you have 1 e to the 15, which is kind of a standard level of diffusion.
Yeah.
And right now I'm doing a factor of 7 where it's the strongest. So it's a profile that looks like this.
Okay. And there's no time step. Well, there's explicit time stepping, so it's okay.
Yeah, it hurts efficiency because of the high viscosity. So I haven't Mark did this as well in his code. Like we took out the Laplacian, made it a separate call. So we only needed to do the boundary, the super subcycling. That's more frequent. With
you do more subcycling up there.
Yeah, with the Laplacian. So we took that out of the hyperviscosity loops for efficiency reasons.
Okay.
But here again, we could pull out the increased viscosity out as well if it needed, since it needs more subcycling.
The increase will need more subcycles.
More subcycles,
yeah.
You do that automatically.
There's some efficiency stuff to look at once we have a scientifically stable configuration with that. But it's just funny that it really absorbs the vertical waves. And funny enough, del2, even with a really high coefficient, it was still unstable for me in WACCM.
Yeah. What was the horizontal resolution?
So 1 degree horizontal and top at 140. When you get up above 100 kilometers, there's some wild gravity wave activity up there.
That sponge layer that we put in, I think straight from you, was didn't work with the high top. It was based on P top. It's like it went from P top to P top times 10.
Mm-hmm.
So if your top of the model is close to 0, the sponge layer was vanishingly thin. It didn't work for us in our 72 layer configuration.
Well, that's weird because it worked fine for 140 kilometers. Maybe I'll send you the formula I'm using.
Yeah, I shouldn't say the one. I should say the one we have doesn't work. I don't know what it is some complicated hyperbolic tangent.
Yeah.
With an arc coat, arc, I forget what it was, but.
It's a legacy from FE.
Yeah.
I guess your original implementation of the del2 sponge was only del or Laplace U and Laplace V, but you missed out on the spherical terms. Actually, the Laplace operator in spherical coordinates has a lot more terms than just the second gradient.
You're talking about finite volume? Because in spectral elements has the true.
Oh, okay. Yeah. Okay. That's done.
The true vector.
Yeah. Okay. Then it's a finite volume sponge, right?
But you're right. In the finite volume, we didn't put in all the terms.
Yeah. Yeah. Okay. Yeah.
Yeah. So, Mark, what are your extra mods for the?
Actually, it might not work.
Noise?
It might not work in your comparison, but it's a topic to be considered. I think MPAS might be in the same boat. It's a filtering algorithm tailored to the discretization. So we do a P2. It's like almost like a phys grid thing, a P2 projection of the topography to keep it in a, it's normally a P3 spectral element. So project the topography down to P2 and then do a little bit of Laplacian smoothing.
Because your modification is to phi s.
Yeah.
Yeah. Okay.
Different way to prepare phi s. So then I can get rougher topography to look even a little bit better than the conventionally smooth topography.
Is that inline or pre-processed?
Pre-processed.
Pre-processed. Okay. Is there any inline smoothing?
In the dicor comparison, Peter was very careful to run all dicors with very similar topography, smooth with the same algorithm.
Offline, yeah.
Offline,
yeah, this is all offline. But I think you mentioned like MPAS has a procedure that they use internally that removes their 2 delta X mode.
Yeah, if I remember correctly, they are using what in our language is 4x smoothing, so 4 applications of the Laplacian. That was more or less where the energy spectra lined up when I was comparing their smoother to the data sets we had. So I think it was 4x. And
okay.
For reference, we're using 16x.
Yeah.
No, well, you're using 16x, and I think we're closer to 8x now.
Yeah.
So I think that's one experiment I would like to run with MPAS is run with the topography they would like to use, which is a lot rougher, and see how that impacts climate, because you'll have more explicit simulation of blocking and so on.
Yeah. Yeah, so I like this one now where we do 1x of the one Laplacian, but this P2 filter, which removes a lot of scales also, but more scale selective than Laplacian.
Mm-hmm. Okay.
So it gives you something like 4x at the low frequencies and then decays steeper at the high wave numbers.
Yeah, I just need to have a dicor ready in a couple of months. Well, actually, I should do my pull request in a month or so. But.
Yeah, well, don't you want to stick with you have this one topography data set that you're using for all 3.
Yeah, I don't want to mess with that now. So yeah. Yeah, that's our challenge here. We need to keep, there are so many factors, so many things we could do, and we need to keep it as fair as we can and as manageable as we can.
I think the problem is they're all going to do a pretty good job on most things, and the decision was really going to be made on different criteria, right? Like strategic planning and resources and.
Yeah, it's a big big equation they have to look at.
I think of the comparison is to make sure there aren't any showstoppers.
Yeah. And then if we're really lucky, some of the idealized results will map onto the full model results, which we don't know at this point.
Yeah, it is probably hard to see the dicor impacts in full-blown coupled. But spin up, I remember there was a spin up issue with SE that it coupled was too cold, or I can't remember. The ocean actually
there was a warm layer
warm.
forming in the ocean,
I
and
see.
we're kind of hoping that maybe the physics grid would take care of it, but it didn't. Well, we haven't spent time on it because we have MOM6. It's going to be the CESM3 ocean model, so we thought to hold off. But that could be a showstopper if we have spin-up issues.
I got to take off a different meeting now.
Yeah.
Enjoy the rest of the meeting, though.
Yeah, thanks for calling in, Mark.
Bye, Mark.
Yeah, bye. But I also think it'll be interesting to have, like, it's not going to be dicor people looking at all this. It's going to be a more broad range of people. So I think it's going to be interesting to see what they find.
Yeah, Gökhan had asked for a time availability. I haven't heard back. Maybe next week. This week seems to be busy.
Yeah, this is a busy time of year. All right, I'm going to go check on the homeschooling.
Yeah,
the boys
I should get some
killed each
lunch
other yet.
here. Yes.
Okay, we'll see you in a little bit.
See you. Bye.
Bye.
Hello, is there anyone on who can just tell me if I'm audible?
Yes, you are.
Okay, thanks.
I stopped sharing, so you can jump to the next presenter whenever you're ready.
So should we think about getting started?
It's fine with me whenever you want us to go.
Levi, you get good points for having some science on your old school chalkboard right behind you.
It's real. Hasn't been tested in a while, but it's a real chalkboard.
Looks like there are people joining, but it is one. So I'd say whenever you're ready to start, Levi, go ahead.
Okay. Let's see. Share screen. All right. Does that look right? Everybody can see the title page?
Yep, I can.
Okay. Oops, went back. All right. Okay, my name is Levi Silvers. I'm a research scientist at Stony Brook University, and I'm looking forward to talking to you all about radiative convective equilibrium experiments that I've been looking at with Kevin Reed, using primarily a couple of versions of the community atmospheric model. So I think probably most people are almost certainly aware of RCE in general, but if you're like me, then you might be a little bit tired of hearing about the 20-odd different MIPs there are. So I'll just remind you all that RCE MIP, number one, it exists, and number two, that's the Radiative Convective Equilibrium Model Intercomparison Project. It got started a little bit later than some of the other MIPs, but the initial results are now out. The data is available, and it's provides a really promising collection of data that I think a lot of us can look into and learn some good stuff from. So the basic goals of the RCE MIP were to try to find out if atmospheric models of radiative convective equilibrium, do they converge to a robust climate state? I think this has been an open question in the literature over the last several decades. Another general goal was to ask what the response of clouds to warming and the climate sensitivity in radiative convective equilibrium is. Another obvious question of that is, even if we know how the climate sensitivity is governed in RCE, does that tell us anything about more comprehensive Earth-like models? And then we also want to know, can radiative convective equilibrium simulations inform future model development? So those are the ideas and questions that drove RCE MIP a couple of years ago. Those objectives are sort of outlined in this paper that I cited at the bottom there by Allison Wing in 2018 and some other co-authors. And the current project that is underway, or that actually the initial results are already done with, it uses a really wide range of models. That's one of the things that's exciting about it. There are global parameterized or GCM models that run RCE. There's also cloud resolving models running RCE. There are large eddy simulations, single column models, and also global cloud resolving models where the convection is all entirely explicit. So the initial results sort of try to summarize results from all of those different types of models, which is really quite a large task. And then as a reminder for anybody who doesn't think about RCE very often, I'll just remind you that it has totally homogeneous horizontal boundary conditions, no rotation, and uniform insulation at each grid point. So the idea is to sort of eliminate large scale gradients and stuff like temperature or pressure so that we can figure out what the balance is between convection and radiation. My screen is acting funny. Okay, there. So I'm not going to really go into the initial results that have been published so far by Wing et al. 2020 and a little bit by this Becker and Wing paper as well. But I do want to just start out by showing you the radiative convective equilibrium. I'm sorry, the relative humidity. I think this is really remarkable. These models all start with the same boundary conditions. They all have the same sea surface temperature. And you can see that they do not come anywhere near converging in terms of their basic climate. We have the vertical profile of relative humidity on the far left for global GCM type models with parameterized convection. And then in the middle here, we have the relative humidity for cloud resolving models. And there's this range in the mid-troposphere of up to 50 or 60%, which has enormous climatological implications. So this is really remarkable that all of these models running the same conditions are so far from each other. I think some people had hoped that there would be a little bit more convergence. So this motivates a lot of good future research. You can imagine if all the models doing RCE showed you exactly the same climate state, it wouldn't really seem like we could learn much from them. The fact that they actually show different states is, I think, kind of encouraging that we can use these as tools going forward for model development. So now to look at CAM-5 and CAM-6, those are the versions of the community atmospheric model that we've used for RCEMIP. So Kevin Reed and Brian Medeiros and probably many more worked a lot to have CAM-5 and CAM-6 be some of the initial models that participated in RCEMIP. So now there's actually a new comp set that was released, I think it was sometime during 2020, where you can run and it makes it easier for the community to run these experiments of RCEMIP using either CAM-5 or CAM-6. And there's 3 different SSTs that are fixed. There's 295 Kelvin, 300 Kelvin, and 305 Kelvin. That's sort of the basic configuration, but of course users could specify other SSTs as well. Like I said, the full sort of initial results are discussed in these papers. And then Kevin is leading a paper where most of the results I'll show you today are coming from this paper that Kevin is leading, detailing an analysis of CAM-5 and CAM-6. So here on the right, I'm showing you just precipitable water from CAM-5 on the top and precipitable water from CAM-6 on the bottom. So these are fully global parameterized convection models with fixed SST at the bottom. I'm going to kind of skip, I'm going to go over this really fast. This was mostly for my own benefit to put this together because I'm new to the CAM community. So I think all of you know this better than I do, but I wanted to point out that both of these configurations use the SE dynamical core, not the FV dynamical core. And I also was quite surprised or interested to realize how many components of the physics changed from CAM-5 to CAM-6. So club, I think, is a big one that most people are aware of. But the deep convection is overall the same. This is my impression, but that there are still some minor changes. The microphysics changed, the orographic drag parameterization changed, and the vertical grid changed a little bit. And then there's a couple new prognostic variables. Again, I'm not going to focus on this much, but I just think it's noteworthy that these models are so different from each other, even though they're part of the same sort of family of models. But in many ways, we found that CAM-5 and CAM-6 look remarkably similar, especially if you recall the figure I showed you of relative humidity with this enormous range among all the different RCEMIP models. On the left here, I'm showing you relative humidity for the 3 different experiments, 3 different SSTs at the bottom. That's what the 3 thicknesses of lines correspond to, is 295, 300, and 305 Kelvin. And you see that the models are very similar to each other in terms of their mean relative humidity. So if you compare the like thickness of lines here, it tells you for the like experiment. And then this is precipitable water again, but this is showing you the anomaly. And it's overlaid on top is the low-level wind field. And so we see that there's wind fields basically of the same order of magnitude. The anomalies are of the same order of magnitude. The size, the dominant size of these anomalies is also similar between the 2 models. So despite basically a total overhaul in the physics, these models are finding a similar climate state for RCE. That's sort of further driven home by some of the mean statistics. We won't look at this table for too long, but I just want to point out that CAM-5 has larger precipitation rates, more precipitable water, and larger cloud fraction and lower OLR compared to CAM-6, but overall they're still pretty similar to each other relative to a lot of the other models that participated in RCEMIP. One of the things, there are two examples where they look very different from each other, and I'll go through those with the rest of the talk. And I think both of those examples kind of demonstrate that radiative convective equilibrium with CAM can be a useful tool to try to figure out how the model really works. So when we looked at the cloud liquid, we noticed that there's this dramatic difference between CAM-5 and CAM-6, where below about 700 hectopascals, there's virtually no cloud liquid. On the left here, I'm showing you the domain mean values. In the center, it's the values in the regions with subsidence relative to or determined by the vertical velocity at 500 hectopascals. And then on the far right is regions with upwelling. And in all of those different ways of looking at this, we see that there's no cloud liquid water for CAM-6. Another important point is that CAM-6, when it does have substantial cloud liquid water, it's quite a bit higher than CAM-5. So the hypothesis is that that boundary layer is too diffuse, the boundary layer that's largely controlled by club, and that it's transporting the cloud liquid vertically out of the boundary layer. This is showing you the range of results from RCEMIP from Alison Wing's paper, and it's kind of demonstrating that CAM-6 is really an outlier. It's outside of the lower quartile, which is marked by these yellow lines. But if we change the width of the vertical velocity PDF in club, we can see right away that essentially makes the models much similar to each other. I don't know if I want to say fixes the problem, because I think that I'm sure that a lot of work went into tuning club for the CESM version of the model. So what RCE tells us is a different question. But in any case, when we decrease that parameter, then we get a lot more cloud liquid in the lower layers for CAM-6, and it looks a lot more, what I'll say, realistic, what we'd expect at least. It doesn't change the higher peaks of cloud liquid though in CAM-6. The other thing that looks notably different between the two models is not fundamental to the two models. It's really just one case for the CAM-6 model, although it seems to be a really persistent case. And that is the warmest case at 305 Kelvin for CAM-6. There's this massive peak in cloud fraction kind of far above the other anvils shown here. Here on the left, I'm showing you the cloud fraction as a function of pressure. On the right, I'm showing you this in temperature coordinates. It kind of shows you the similarity between the models in a different way. Here you see that the relative humidity of that one case goes all the way up to 100%. And then here you see, again, just cloud fraction, but plotted in temperature coordinates. So this is one of these things that's really hard to ignore. I mean, when you see this in the RCEMIP paper, this case really jumps out at you, and it throws off a few of the other statistics. And so we spent some time trying to figure this out, but we still don't have a great handle on why this is happening. We do know Kevin ran a few experiments where he decreased the ice concentration number, and that, as you might expect, led to reductions in the upper level cloud fraction for this case, but we don't have what I would say a thorough understanding of why this happens for 305 and not for 300, for example, or why it doesn't happen in CAM-5. We'd actually love input from anybody who might have an idea on why that's happening. However, I don't think that this is really driving major differences in the climate. This one outlier case, for example, if you look at the outgoing long wave radiation, which is shown in the gray and white tones here, you really can't tell a major difference between CAM-5 and CAM-6 in either the precipitation or the OLR. And the table that I showed you previously, it also does not indicate a major difference between these different experiments. And so I think that this is a super thin layer of ice crystals very high up in the atmosphere that is presumably not driving the climate. Another thing that I think is noteworthy and would help us utilize the RCE experiments is if we could kind of connect how those relate to the larger system, to the CESM models and the Earth-like models. So you can ask the question of how similar are the clouds in RCE to those in CESM1 and CESM2. So here I've taken the cloud fraction that I showed you in the previous slide, and I just went and grabbed, I have to sort of double check all of these figures. I've been doing this just over the last couple of days, doing my best to figure out this file structure in GLADE, but to the best of my knowledge, this is the pre-industrial control example or CMIP experiment for both CESM1 and CESM2, where I just took a quick global mean and looked at the cloud fraction. And here we see that the low-level clouds are quite similar between CESM1 and CESM2, kind of in opposition or different to this RCE case. But as many of you are aware, RCE is really more indicative of the tropics. And so then if we hone in more on the tropics, we start to see more meaningful differences that are similar to the RCE case. So here the thin lines are the case for plus minus 30 degrees around the equator. Then when it gets a little bit thicker, that's showing you plus minus 10 degrees around the equator. And then the thickest lines are showing you plus minus 5, so really the deep tropics. And in the deep tropical case, really in most of these cases, but especially the deep tropics, we see this difference in low-level clouds that we first noticed in RCE also comes out from CESM1 and CESM2. And also there's lower and kind of stronger anvil clouds in CAM6 or CESM2 as well. So this is, I thought that this was kind of interesting that it does seem to be matching the clouds that we're finding in RCE as long as we focus on the deep tropics. Then here on the left, I did the same thing with the AMIP experiments. And we find the same type of cloud structures as you might expect in AMIP as we did in PyControl. This also shows you though that the coupling with the ocean doesn't really fundamentally change the deep tropical clouds. But in any case, CAM6 really is producing far fewer clouds below 700 hectopascals than CAM5. And then the last thing I wanted to sort of show you is that it's interesting to think about climate sensitivity and ask what we can learn about the climate sensitivity of the Earth-like models from RCE. And that's really still an open question. And so far, RCEMIP has not answered that question. So I think there's a lot of good research going on right now. But here I've sort of compiled some of the numbers that appear in the literature over the last number of years. There's a lot of papers on this with the CAM models. So I'm sure I'm missing tons of information here, but I started with some of these papers that Andrew Gettleman led, and we can see this pretty well documented case of the CAM models as the version increases in time and complexity. Essentially, the sensitivity increases from 3.2 Kelvin to 4 Kelvin to 5.3 Kelvin. And we see the same thing in aquaplanets, where if we look at this example of the CAM4 aquaplanet, there's a sensitivity of 1.7 Kelvin. The CAM6 aquaplanet, which I grabbed this from the published data for CMIP6, the sensitivity is 2.5 Kelvin. And then here's the cases that I was talking about earlier today of the RCE, where we have going from 295 to 300 is the first number, and 300 to 305 is the second number. And so the pattern here is not quite as simple as what we're seeing up here, and I think this could be connected to some of the cloud cases, but it basically indicates the need for a little bit further research. In one case, CAM6 is more sensitive than CAM5, in another case it's not. And so that could be due to the outlier case, but we need to look into it a little bit more. So to conclude, I think one of the main things I want as many people to know as possible is that there's a new comp set. And so this should hopefully make it a lot easier for other people to run RCE experiments and to explore some of the interesting features and findings in those experiments. The experiments are pretty inexpensive, and they provide a really useful framework for testing parameterizations, but also trying to help us advance our understanding. And I'm going to say club here, but it really is CAM6. I guess I can't definitively say it's club, but it appears to decrease the cloud fraction and nearly eliminate the cloud liquid in the tropical lower troposphere in RCE, PyControl, and AMIP. So I don't know, does this mean that club is overly diffusive in those circumstances, or is there something else going on? And then we have a couple of papers that are sort of in the works, in the pipes, documenting a lot of what I just showed you today. That's it. Thanks for your attention.
Okay, thanks a lot, Levi. We're a little bit over, and in the interest of time, there's kind of an active active discussion going on in the chat section, so maybe.
Yeah, I'll go ahead and mute myself, and then I'll go into the chat section and answer questions as I can there.
All right, and we'll have a discussion session at the end of, I think at 3 this afternoon, so people can also ask questions then.
Okay, thanks.
Thanks a lot.
Yep.
So I think we're going to move on then to the next talk, which is by Kyle Nardi. Is Kyle here?
Yeah, so I'll share my screen.
Okay.
All right, so hi everybody. My name's Kyle Nardi. I'm a PhD student here at Penn State working with Colin Zarzicki. And the work that I will be presenting here is in support of the Momentum CPT. And I'm specifically focusing on tropical cyclones and how we can improve the depiction of the tropical cyclone boundary layer in CAM-6. So the motivation for this work is that CAM-6 produces several notable biases in the structure of the tropical cyclone boundary layer. So one notable bias is that the jet height, or the height of maximum tangential wind in CAM-6, which is depicted here in blue, it's 1 to 2 kilometers too high compared to LES, which here is CM1, which is shown in red, and then also observations, which are shown in gray. We'd ideally like to have the height of maximum tangential wind somewhere around 1,000 meters. But as it stands now, at peak intensity, CAM-6 produces a height of maximum wind somewhere around 2,000 to 3,000 meters. So that's something we obviously want to lower. And then at the same time, there's a bias in some of the thermodynamic quantities in the boundary layer. So notably, CAM-6 produces a boundary layer that is too warm, and it's also too dry, or at least it's too dry below 200 meters. It's actually too moist above 200 meters, but I want to focus on the lowest several hundred meters because those are most important for the surface heat fluxes from the ocean to the atmosphere. And what we see is that this warm bias produces a sensible heat flux in CAM-6 that is too low, and then a latent heat flux that is too high due to this dry bias. And that produces a latent heat flux fraction that is well too high in CAM-6 compared to large eddy simulation. And actually we get values that are greater than 1, implying that the sensible heat flux is negative and the heat's actually going into the ocean, which isn't realistic. So in this talk, I'm going to focus on these 2 particular model biases, but I do want to point out that these aren't the only biases we see, but for the sake of time, I'll just focus on these 2. And ideally, we want to reduce the height of maximum tangential wind and reduce the latent heat flux fraction. So the working hypothesis here is that we can reduce some of these model biases in the TC-PBL structure in CAM-6 by perturbing some tunable parameters in the parameterization of momentum flux, in this case via club. And then the main question is, given the large number of potential parameters that we could change, how do we objectively identify parameters that are the most important in a computationally efficient manner? And to do that, we perform a sensitivity analysis that calculates the effect of changing particular inputs in club on the model output. In this case, for instance, height of maximum wind or latent heat flux fraction. And we specifically use the Morris one-at-a-time method, which is well documented, and I don't have quite enough time to go into the exact details, but what I do want to point out is we choose this particular sensitivity analysis because it's computationally efficient and it allows us to perform this analysis while running a limited number of model runs. And essentially the way this works is we have a set of inputs, and you can think of these as tunable club input parameters. And we vary each of the inputs within a set of discrete values. And then we run a number of configurations where we have unique combinations of the inputs. And from one run to the next, we keep everything the same except for one particular input. So from run 1 to run 2, everything's the same except for changing the value of D. And then from run 1 to run 2, we can look at the output Y, like the height of maximum wind, and we can see how much of an effect per unit changing D had on the output. And then from this, we can derive a ranking of the relative importance of each particular input parameter. And so we're performing this sensitivity analysis using idealized configuration of CAM-6. So it's an RCE type configuration. And what I really wanted to point out are two, or actually three main changes that we're implementing here. So first, we're imparting a drag saturation at high wind speeds, similar to Large and Jaeger, and that produces profiles of the drag coefficient that are more realistic at high wind speeds for tropical cyclones. And then the other changes are actually directly in club. So first, we're using a prognostic equation for momentum flux, as opposed to the diagnostic eddy diffusivity formulation that's traditionally used. And then we're also diagnosing the turbulent length scale using the eddy time scale, or in particular, the inverse of the eddy time scale. And that formulation is based on certain characteristics of the environment, such as the vertical wind shear, buoyancy, and then proximity to the surface. So this is a list of the input parameters that we are changing, and I wanted to highlight these four particular experimental club input parameters. These C inverse tau terms are essentially coefficients in the formulation of 1/tau, which is then used to calculate tau, which is then directly proportional to the turbulent length scale. So we expect changing these coefficients will have some influence on the turbulent length scale and the degree of mixing that we see in the boundary layer. So now once we've run the Morris analysis, the sensitivity analysis, we're really looking for two desirable characteristics of the inputs. So first, they have to produce a strong response. So when we change the inputs, we want to have the output, like height of maximum wind, we want that to change appreciably. But at the same time, just as important is the direction of the response. So we want the height of maximum wind to go down. So we want to be confident that when we're changing one of these input parameters, we are getting the directional response that we want. If in some cases, the input is increasing the height of maximum wind half the time and then decreasing it the other half of the time, that's not very useful for us. So we ideally want to find input parameters that consistently decrease or perhaps increase the particular input, so we're more confident in the directional response. So in these plots here, we're looking at sensitivity. And if you see an input parameter in this corner of the plot, that implies that the height of maximum wind is relatively sensitive to that input. And then this plot here shows the directional response. And the way you interpret this plot is any input parameter in this corner here, that implies that when we increase the input parameter, we are consistently decreasing the height of maximum wind. So 90 to 100% of the time in this analysis, when we increased these input parameters, we are decreasing the height of maximum wind, which again is what we desire. Now, this is a summary of this analysis I showed here, but for all the different output metrics that we analyze. And I won't go too much detail about this, but I do highlight ZV max, which is height of maximum wind, and latent heat flux fraction. But we also looked at sea level pressure, the radius of maximum wind, the area of the cyclone. And what's really important here is that we're looking in this plot, this is a sensitivity plot. So any dark shadings here, that's implying that the particular output is highly sensitive to the input. So we ideally want to find these darker colors here for ZV max. But we also need to match it up with the directional response here. And any dark color you see here, that implies that you're getting a consistent directional response. The deep reds meaning that you're consistently getting a negative response or a decrease in the output. And then deep blues mean you're getting an increase consistently. So ideally, you want to match those two up. So again, summarizing the last few slides, we're looking for input parameters that are highly influential, and when increased, they consistently decrease the metrics. So we're looking for dark colors here and dark colors here. Now, one particular input parameter that we identify is C inverse tau shear. And again, this is one of the experimental club input parameters that's attached to the vertical wind shear term in the formulation of 1/tau. And from the Morris analysis, we expect the height of maximum wind to consistently decrease when we increase C inverse tau shear. And then we expect latent heat flux fraction to decrease as well. And these are different simulations where the only thing I'm changing is the value of C inverse tau shear. Darker colors are lower values, and then the lighter colors are higher values. And what we see, as the sensitivity analysis tells us to expect, we're getting a decrease in the height of maximum wind and the latent heat flux fraction, which is what we desire. And we're getting closer to the LES simulation in red. So the question is, why exactly are we getting this response? So again, C inverse tau shear is associated with vertical wind shear, which we see a lot of in lower levels of a tropical cyclone. And increasing C inverse tau shear has the effect of essentially increasing the amount of turbulent eddy dissipation due to vertical wind shear. So we would expect 1 over tau to increase, and then we'd expect tau to decrease, and as a result, the turbulent length scale we would expect to decrease, which is what we see here. So this is a radially average cross-section, and anywhere you see red, that implies that increasing C inverse tau shear reduces the magnitude of the particular quantity that's being plotted. So this here indicates that when we increase C inverse tau shear, we get a strong reduction in the turbulent length scale, and then also associated with that, a reduction in the effective eddy diffusivity and TKE and the vertical momentum flux. So essentially we're getting less mixing in the boundary layer in this situation. And that has an influence on the wind profiles then. So this is tangential wind, and what we see here is a reduction in the tangential wind here around 3,000 meters, and then an increase here around 1,000 meters. And this dipole implies that we're getting a downward and an inward shift in that low-level jet within the tropical cyclone. And you can also see that in the radial inflow. So we're getting reduced radial inflow here, but then increased down here, implying that downward shift. And then we're getting an inward shift in the peak updraft associated with the eye wall convection. And this is consistent with other modeling studies that have found that changing the amount of vertical mixing can change the height of maximum wind. So that's one influential aspect. And then when we look at the latent heat flux fraction, we can explain that by this notable cooling that we see below 1,000 meters when we increase the inverse tau shear. And what that's going to do is going to then increase the sensible heat flux from the ocean to the atmosphere. And at the same time, we're getting this modest moistening below 1,000 meters, and then we're getting drying above, likely because we're getting less advection of moisture up into these higher levels with less vertical mixing due to increasing C inverse tau shear. And what that's doing is it's then decreasing the latent heat flux, which is then going to decrease the latent heat flux fraction overall and get us closer to LES and observations. And I'll just leave with my key takeaways here. So the sensitivity analysis can allow us to objectively identify some output metrics that we can consider influential for the tropical cyclone boundary layer. And then some of these new updates to CLUB can help us sort of sculpt the profile of momentum flux based on the specific atmospheric regime. And then decreasing vertical mixing and eddy diffusivity in CLUB seems to produce more realistic tropical cyclone wind profiles based on observations in LES. So I think my time is up. So that's all I have. So I'll take any questions if there are any.
It looks like Chris Cruzy and Andrew Gettleman have questions. Chris has showed up first. Do you want to go ahead, Chris? Well, he's not. He's maybe he's muted. I'll just.
Sorry. Yeah, I was muted.
Go ahead.
I was just wondering if there was a way to estimate the turbulent time and length scales that you are using within CLUB, and if there's any sort of data that you can compare them against.
Yeah, so I don't have plots in, so we are analyzing that. So we're specifically parsing out the contribution of each term. So there are 4 terms in the formulation of 1 over tau. So it's vertical wind shear, it's buoyancy, there's like a overall background term, and then there's a near surface term, which increases as you get closer to the surface. And we've done an analysis looking at which component contributes the most to the resulting length scale. And I think the surface term, I think, contributes the most. But then in the tropical cyclone specifically, where we do have the high vertical wind shear near the surface, we do get a high contribution from that. But that's something we're working on now, or then we're comparing it to LES, and we can look at the turbulent length scales that CLUB gives us, and then what LES might give us, and then we can make a comparison there to, again, better tune the coefficients and sculpt the actual values of tau based on how much of a contribution there is, from the vertical wind shear or the buoyancy. So I don't have plots for that here, but that's something we are working on.
Okay, Andrew, you want to go ahead? I think we're going to have to cut it off. Peter and Andrew both have Peter Caldwell and Andrew Gettleman have questions. I think we'll just take those two and move on. Yeah.
I mean, I don't want to steal Peter's thunder, but they're sort of related as to whether you've done any looking at this in a full version of CAM-6 just to see if it improves TCs. And then Peter's question is also a great one of, does it do anything else to the climate?
Yeah, so actually, so that's a great question. So I actually didn't put this slide up. That's one of the next steps. So testing this in a more realistic global climate simulation is the next step. So we want to get a good sense of what's going on in this sort of idealized RCE world, and then go into the global climate simulation. So I would say stay tuned for that. That's definitely something we are going to be analyzing, because that is a major concern. Obviously, if we're improving, the depiction of the tropical cyclone boundary layer, are we doing something else to the global climate? But that's something that will be down the road. So we're getting to that point. But that is something we're certainly considering. It's a good point to bring up.
Okay, thanks, Kyle. I think in the interest of trying to stay on the schedule, at least partially, we'll move on now to Sean Santos, and if there are more questions for Kyle, put them in the chat. So I can see your slides, Sean, but I can't hear you. Sean?
I was just muted, sorry.
Oh, okay.
Okay, I thought my microphone was broken again. Okay, so I'm Sean Santos. I'm going to be talking today about time integration error in the E3SM atmosphere model. I'm broadcasting to you from my pandemic office in someone else's bedroom. So this is work that I did with Peter Caldwell and Chris Brotherton at the University of Washington. There's a James paper that the beginning part of this talk is going to draw from, and then there's some more sort of hot off the presses preliminary stuff for the second half of this. So first we're going to start off just talking about some of the global effects of changing the time step in the E3SM atmosphere model, which is broadly uses the same parameterizations as CAM-6. So we want to know how much does the choice of time step actually matter. The easiest way to find out is to change it, and to change it by a lot. So we've done two 3-year runs at standard resolution, 1 degree. We used an F1850 COM set, so this is at the data ocean. One of these runs uses the default time step, which is about half an hour, or it is half an hour for the dynamics physics coupling and much of the physics. Our modified run, which I'm going to call all 10, uses a time step of 10 seconds for everything. So we set D time to 10 seconds, and also all component subcycles are disabled, so everything's running at the same time step, except radiative transfer is still calculated every hour. So there's a lot of changes from that, especially related to things like the cloud radiative forcing, but I'm going to focus here just on precipitation. So if you look at precipitation, one of the first things you notice is that there's an increase basically everywhere in large scale precipitation. The increase is strongest over tropical land and mountains. So if you reduce the whole model time step to 10 seconds, you get up to 50% increase in total rainfall in these areas. The convection precipitation decreases to partially cancel this out, also increases in some regions. So if you look at total precipitation, there's this more complex plot, but you still get these intense increases over tropical land. You also see that when you reduce the time step, you get much more extreme values for hourly precipitation. So this is, you can think of it as basically like a PDF, like how much precipitation is falling in events of given like hourly precipitation. So you can see the control run in black almost never has significant precipitation over 100 millimeter per day rate, whereas actually a large proportion of the precipitation in the all 10 run comes from precipitation of events that are that intense. Another thing that we looked at is the residence time of water in the atmosphere. So you can just take the global precipitable mean precipitable water over total precipitation. In the control run, that's about 7.3 days. For the all 10, that's only 6.9 days. So a way to think about kind of what's going on for the overall water budget here is that the enhanced precipitation is drying out the atmosphere. And since we have a reduction in convective precipitation, we think that's probably either due to changes in dynamics club interactions or increased, which would cause more condensation, or increased microphysical precipitation efficiency, causing the clouds to rain out more quickly, or some combination of the two. So in order to get at what's going on from a more process-oriented perspective, we also looked at changing the time steps for the individual processes in the model. So we had this control run, it's the default. We have the L10 run where everything is changed to 10-second time step. And now we're going to go and we're going to make runs that have just club at a 10-second time step, or just MG2, or just the dynamics and so on. Because there's a lot of these different runs and we had limited computational resources, we just ran these for 30 days. For various reasons, we ended up comparing variables mainly from days 3 through 15. Because these are such big changes to the physics that you see at these lower time steps, you actually see pretty clear differences between these runs from that fairly robust changes that match up with what you would see in the full 3-year run. So some of the time steps that we changed that didn't have much of an effect were, first of all, the SE dicore. Secondly, if you just change the club time step by itself, that does not have all that much of an effect. And also the radiative transfer calculations. So we did try doing those every time step. Even if the time step is down at 10 seconds, it doesn't seem to have much of an effect on the run, at least from these like global averages that we're looking at. Just briefly, so if you look at these 50-day runs and we just, again, compare the all 10 to the control, we see a global average increase of large-scale precipitation of 0.26 millimeters per day, a global decrease in convective precipitation of 0.21 millimeters per day. So that reflects the overall increase in precipitation that we saw, and also a large repartitioning of precipitation from the ZM deep convection scheme to the large-scale precipitation produced by club and MG2. There's a paper by David Williamson from 2013 that explains what we think is at least part of what's going on here, which is just that when you have more frequent coupling, the combination of club MG2, these kind of hard saturation adjustment that's getting rid of supersaturation in the model for CAM4 was able to outcompete ZM. And in this case, we think club and MG2 and CAM6 are also able to outcompete ZM for available water vapor when you're using a short time step. So if you change just the MG2 time step rather than the entire model, you do get some of the same effects. They're just reduced in magnitude. So you get about the same amount of increase in total precipitation, actually, and then a somewhat smaller repartitioning from convective to large-scale precipitation. This is consistent with the idea that we have an increase in precipitation efficiency that's causing that. There's also a potential explanation for that in terms of rain evaporation basically being very strong at the default time step. And when you reduce the time step, the rain evaporation goes down, more of the rain reaches the surface rather than being recycled back into the atmosphere but through evaporation. And so that is having some effect that's causing these change in total precipitation and residence time of water in the atmosphere. So we have at least a pretty plausible explanation for that we need to look into more. Changing the time step of club and MG2 together actually adds quite a bit more repartitioning. So we again see bigger increases in large scale precipitation, less convective. It's not really clear to me why. I think the more clear and interesting aspect of what happens when you change the time step of club and MG2 together is you see these increases in extreme precipitation and the changes in the spatial pattern distribution of precipitation that we saw. So to get a fairly clean comparison here, these are 2 runs compared to the control, both of which have default time steps for everything except club and MG2, which are both running in 10 seconds. So the only difference between these runs is in the left one, they're coupled at a 5-minute time step, which is the default in the model, even though they're running at 10 seconds each. And on the right panel, they're coupled every 10 seconds. And we see these signature changes in basically increases in large scale precipitation over the land showing up near the Andes and over the maritime continent that don't show up if club and MG2 are not coupled together. Now I'm going to talk a little bit about just some case studies from South America that may clarify a little bit what might be going on there. So first of all, I did look at, for all of these runs, just what's the highest precipitation, the column with the highest precipitation on day 1 in South America when you have club and MG2 substep together. So relatively little precipitation falls here in the control simulation, which is in black. Also, if you couple MG2 and club at a 5-minute interval, even with reduced time steps, you get the dark red, which still has relatively little precipitation compared with the other runs. If you have club and MG2 substep together, you get much more precipitation. And if you couple the entire, or if you run the entire atmosphere and land model at 10 seconds, that's the gray, where you have double the precipitation that you see in the other runs. So this is all day 1. They're starting from the same initial conditions. And so this type of event, I picked one in particular here, but this is a pretty common pattern comparing these runs short while into the simulation where there's a lot of precipitation. This seems to be driven basically by condensation and condensational heating. So in the first column here, what I'm showing is results from the 5-minute club MG2 coupling. This is the 10-second club MG2 coupling, and this is the whole atmosphere being at 10 seconds. So the top is condensation, the middle is vertical velocity, and the bottom is rain production. So you see, so this is over time and altitude. There's very little condensation actually occurring when you couple club and MG2 at the default time step, but when you decrease that to 10 seconds, you get a lot more. And when you allow the dynamics to be coupled at the same time step, it's a really serious difference. So just looking at time, I'm going to skip really talking about this slide to detail. Just another unrelated effect that I see looking at day 1 in South America is extremely oscillatory 10-meter wind speed, basically over the whole continent. And this is something you would only see if you have every half-hour outputs. But there seems to be serious numerical instability in the way surface stresses are applied, which can affect the latent heat flux. So conclusions, E3SM's atmosphere model has significant problems with time step sensitivity, which I expect many apply as well to CAM-6. There's a question that's been with us for a long time, which is, what should CM be doing at short time steps? How should it be balancing its convection with clubs? And there's also questions of if you need sub-minute time steps to resolve your microphysical processes. How do you deal with that? We don't really want to run much parts of the model at sub-minute timescales. So we need a different time integration strategy. We do have this bizarre coupling effect between club and MG2 that leads to these intense high precipitation storms. It's not clear if this is just something that you would tune away if you change the model time step, or if there's some more serious conceptual issue in the way club and MG2 are coupled. And there's signs that there's instability, that half an hour is just too long for coupling between surface stress calculations and the boundary layer diffusion. And I think that's it. I'd like to acknowledge these people for their contributions and their funding. And here's some relevant papers.
Okay, thank you, Sean. I don't see any questions in the chat right now. I'll just ask a quick one, and then maybe we should move on. So when you change a time step, you haven't changed the relaxation time used in Jan-McFarland, correct? So is being scaled by the time step over this relaxation time.
That's correct. Although I have tried, and Huiwan I think has also tried experiments where that time scale is changed. It does not do a very good job of canceling out the effect of the time step change.
Okay.
In fact, it makes some of the biases some of the changes actually more dramatic.
All right. Okay, thank you. So if there are more questions to, well, I see something just appeared from Keith. I'm gonna ask Sean and Keith to answer look at this question on the chat so that we can move on. We're 5 minutes late and try to keep us a little bit on schedule. So I'm gonna thank you again, and I think we're gonna move on to Jack Chen's talk. Jack, are you here?
Yes.
Okay, great. I don't know what time it is for you, but
I'll share my screen.
okay.
Thank you.
Sure.
So first I'd like to acknowledge my collaborators on this project, Yaga, Mitch, and Shanghai at RAO. So the goal for this talk is to talk about the work we've done the past year or so, which is to introduce a new parameterization to represent a physical process which is missing in most GCMs, namely mesoscale convective systems. So here's a plot for that. Basically, in the presence of mesoscale convective systems, you get a cooling effect in the lower troposphere by mesoscale downdraft and a warming effect aloft by the overturning ascent. And the parameterization is usually called multi-scale coherent structure parameterization, or MCSP. So the heating tendency we add in to represent this circulation as in B. So you introduce a cooling effect down in the lower troposphere and warming effect aloft. The formulation is pretty simple. Qm being the heating tendency from the mesoscale heating is proportional to Qc being the average heating from the deep convection scheme, and alpha 1 being a free tuning parameter. So we conducted high resolution work simulations to determine what alpha should be. So we picked like 2 MJO episodes and showing in the 2 panels, the black curve being the total heating tendency within the computational domain, and the red being the heating tendency from deep convection, and the blue being the so-called stratiform heating tendency, or the mesoscale circulation I just showed earlier, which is missing in CESM. And with these two simulations, we determined alpha 1 should be between 0.3 and 0.5, which we try in the simulations in CESM2, as well as actually in E3SM. And also we add a wind shear trigger because mesoscale convective systems tend to form in the presence of vertical wind shear. We tried 3 different values, 3, 5, 7.5. The wind shear being the zonal wind difference between the surface and 600 hectopascal. And when you, so basically the wind shear has to be higher than wind shear trigger to trigger the MCSP parameterization. So just to explain how this works, if you set the wind shear trigger bigger, then you're less likely to trigger MCSP. And if you set the wind shear trigger being 0, that means when you have deep convection happening, MCSP is triggered at all times. So first, I would like to talk about the average heating in the tropics. So the left panel showing the heating tendency from the MCSP. The blue being alpha 1 being 0.5, the red is alpha being 0.3. So there's no surprising here. So you get more cooling, more heating when you set alpha 1 larger. But surprisingly on the right panel, this is the total heating, including the ZM scheme. Down below, the blue and the red showing less heating. That's not surprising because we add cooling in the lower troposphere, but it's probably not very easy to see, but I'll point out at about 600 hectopascal. The blue being the weakest heating. Of the 3 cases, the black is the control run, where we actually add heating to the scheme. This implies when you add MCSP in the model, you are going to reduce the occurrence of deep convection. And that is why you reduce the average heating from the ZM scheme, which has a lot of implication in the simulations I'm going to show later. By the way, I'll point out the reason being when you add the cooling down below and heating above from the MCSP, you are going to stabilize the atmosphere a lot more than the ZM scheme, and that's probably why you see what happened on the right panel. So first we examined the Wheeler-Keledes diagram, and showing is the spectra from precipitation, and this is from CAM-6. I'll focus on Kelvin waves, which is quite a bit weaker than observation. And when we include MCSP in different configurations, it's showing it enhances the spectra of Kelvin waves. And we see the same thing in EAM, or the atmosphere component of E3SM. And next, we'll look at the MJO spectra. Showing is the OLR spectra in the Burrow winter. And compared with observation, the baseline CAM-6 showing weaker spectra within the window of 30 to 90 days. As you can see, when we include MCSP, the spectra within that window increases. And quickly, I'll show in EAM, it's the same thing. Next, I'll show the couple simulations in CESM2. I was a bit surprised to see this, the control simulation showing actually weaker spectra for the MJO within the 30 and 90-day window. However, when we include MCSP, the spectra within the 30 and 90-day window It's much stronger. The response is much stronger than in CAM6 and much closer, actually gets stronger than observation now. And it's showing the same thing in E3SM. So it seems to be, we have two models comparing side by side, and we're showing, seeing the same behavior. So the result seems to be fairly robust. And here's the life cycle composite plot for the MJO. And the color shading is OLR perturbation. As you can see, the convective systems propagating from the Indian Ocean into the tropical West Pacific. That's from the OBS. And for the control run, the baseline CAM6, first, the perturbation, the OLR perturbation is very weak. And then it's also showing when the convective system gets into the tropical West Pacific, it stays stagnant and then have trouble getting out. While when we include the MCSP, the propagation seems to continue into the tropical West Pacific. And also the OLR perturbation gets stronger, even though still weaker than observation. And here's the results from AAM, showing very similar results as in CAM6. For the couple simulation CESM2, this showed eastward propagation, but just like in CAM6, the OR perturbation seems to have trouble getting into the tropical West Pacific. It kind of dies when the convection enters the zone. While when we include the MCSP, the propagation continues and gets much closer to observation. And in E3SM showing the same thing. Here we examined precipitation biases. I'll just focus on the middle row. The first plot is DJF biases introduced by CAM6 compared with GPCP. So I'll just point out in the tropical West Pacific, there's positive precipitation biases introduced by CAM6. Same thing in the tropical East Pacific. And the three panels on the right are from the simulation of MCSP. And this is biases compared with CAM6. So it is basically showing negative biases against CAM6. So MCSP basically corrects the positive biases in the tropical East and West Pacific. This has a lot of implication in the MJO diagnostics I showed earlier, because the strong positive biases introduced by the baseline model, especially in the tropical West Pacific, seems to imply the convection in the region being too persistent. And MCSP makes the convection in this region less persistent. That actually allows the convective system to continue to propagate eastward. In EAM, it's showing very similar results as in CAM6. And this is from CESM2, again, showing very similar results, especially in the tropical West Pacific. The positive biases in CESM2 being corrected by MCSP. Again, E3SM showing the same thing too. So I go by my talk pretty quick. So here's the summary. So we've implemented a new parameterization to represent mesoscale convective heating. And we use high resolution work simulations to determine the exact the magnitude of the heating. And the implementation of this parameterization improves Kelvin weight generation and strengthens the MJO. And as I talked about earlier, the MJO propagation is significantly improved in tropical West Pacific. And the parameterization does that by enhances the stability of the atmosphere, making convection less persistent in that region. And the new parameterization also reduces the positive precipitation biases in the tropical West Pacific as well as in the East Pacific. And I will actually emphasize this point when I was revising a manuscript on this work. That is a review paper by John et al. 2020. A lot of times when you try to improve the MJO representation in GCMs by tuning the model, it usually leads to degrade the mean state. And in the paper, it actually shows various approaches using the MCSP a better approach, meaning you don't degrade the mean state. As shown earlier, it actually simultaneously reduces tropical precipitation biases, also improves the representation of MJO in the model. And currently, we're adding another component in the representation of mesoscale circulation, that is momentum transport. And that's all I have today. Thank you for your attention.
Okay, thank you, Jack. There's one question on the chat from Rich, and Judith has her hand up. We are running a little late, so I think those two will be it. Everything else can be on the chat.
Sure.
So, Rich, why don't you go ahead?
Yeah, I'm just wondering, I think I've asked Mitch this before, but I was just wondering whether the changes you see, do you know that they're not due to just a shift from the convective to the large scale, or is there a real shift in the vertical of where the heating comes from, and then that's just, and that in the same situation where the large scale precip is the same?
We do see a reduction in tropical convective precip. So the reduction we see in the precip is mostly due to the reduction of convective precipitation. So I think it reduces the occurrence of convection, actually.
Right, because in the past, yeah, I mean, I look at this top line there, the red dots there have been indicative, particularly in summertime. Is that summer? Yeah, in summertime of a much increased large scale precip. So
yeah, for JJA, we do see like this is I'm showing this panel here. JJA, it does kind of enhances the positive biases, but this is probably related to summer monsoon here.
Yeah, absolutely.
And it might require a different kind of parameter to prevent that from happening. Yeah, we do notice that, and we don't actually go about to address this at this point. Yeah, that's a good point, because I think the treatment for the summer and the winter seem to be different, should be different. Because, yeah, like I mentioned, for JJA, it seems to actually degrade the mean state.
Thanks.
For summer monsoon.
Okay, so why don't we, if Judith is still, yes, her hand is still raised. Judith, do you want to ask your question? Especially, we should probably try to make it quick because we are running late. Judith? Okay, Judith says she's going to ask her question in the chat. So at this point, we're going to change sessions. I think Xiaohong will will take over for the next session on aerosols, and we'll have a discussion after that. I apologize on behalf of all of us co-chairs. I think we somehow neglected to build a break into this afternoon, but anyway, we're gonna move into the aerosol session now. So I'll let Xiaohong take over.
Okay. Elizabeth, could you assign me to the co-host? Then, so our next, we are going to have 4 talks, and then after that, we are going to have a discussion on cloud and aerosol. So the first talk is given by Ziming Ke. He's talking about the MEM5 and on the WACCM simulation. Ziming, are you ready?
Yes. You hear me?
Yeah.
Okay, I will share my screen. So could everyone can see my screen?
Yes.
Okay, cool. I'm Ziming Ke. I'm a postdoc, worked in Dr. Xiaohong Liu's group in Texas A&M University. Here I want to present the work about the MEM5 and our evaluation of MEM5 in the CESM 2.2 WACCM. Before beginning, I want to thank the co-authors, is Dr. Xiaohong Liu and Luisa, Simon, and Michael from NCARS. So this is the work I want to talk about today. First, I want to talk about the MEM aerosol scheme in the CESM and the change of the MEM4 between the CESM1 and the CESM2. Then I will talk about how we will modify the MEM4 to MEM5 and what we want to achieve. And last, I will talk about the results about the MEM5 performance. We have 2 simulations is under the historical run and also under 2000 climatology run. First, what is the MEM aerosol models? That is a model aerosol model. In this model, we assume aerosol be divided in different groups, like we see here by different colors of lines. For each group, that aerosol will be determined by 2 main characters. One is the diameter, and the second is the sigma g. Diameter is the mean geometric diameter, and the sigma g is the geometric standard deviation. That sigma g will determine the width of each aerosols. I mean here, the width. The smaller sigma g, we will get a smaller group size, and the gravitational settling also will be smaller. So to determine the values for different aerosol groups, a good summary is given by Easter 2004. And he organized the different observations for different size of the aerosols. So this is the aerosol parameters we used in CESM1 MEM4. And since CESM2, there is some changes. The biggest change is occurred in the course mode. The standard deviation was changed from 1.8 to 1.2. So as we said, we get a smaller standard deviation, we will get lower gravitational settling. And then the size also changed in CESM2. So there is a reason behind these changes, because the Pocola and English in 2009 and 2013 reports by using sigma g 1.2 to 1.3 can better simulate the stratosphere, the aerosol in the stratosphere after the big volcano eruptions. Mike Mills adopted these changes in the CESM WACCM and shows very well reproduced the stratosphere sulfate burden. However, in the troposphere, as the original value is 1.8, Wu 2000 and Li 2020 reports in CAM6, the dust distribution is not good as in CAM5. So here is we begin to think about a better treatment to treat the aerosol in both stratosphere and troposphere. So our modification is straightforward. We create a new stratospheric course mode for the sulfate aerosol, only for the sulfate aerosol. Then the purpose of that is we can use this small standards, the standard deviation 1.2 in the stratosphere for the sulfate aerosol alone, and we only add 2 tracers. Then we bring back the old course mode setting in the CAM5, that is CESM1 MAM4. Some minor changes in the CESM2, we will keep it for convenience. So one change I needed to mention is in previous CESM2 MAM4, we will have a renaming process. Sorry, is between the accumulation mode and the course mode. This renaming is designed to transfer the accumulation mode sulfate to the course mode in the stratosphere. But also this renaming process, due to the code reason, also will transfer dust and the CESO. That will also prolong the dust and the CESO's lifetime and significantly in the stratosphere. So in our design, we only transfer the sulfate in the stratosphere. Okay, so how to test our results? First, we test the MAM5 whether it can reproduce the sulfate aerosol burden in the stratosphere after the volcano eruptions. Second, we check how the MAM5 will impact the sulfate dust and CESO in the troposphere. Before we do the evaluations, we need to retuning the model to get the balance. So the dust and the CESO, both emission have tuning factors. We want to keep the two model as similar as possible. So we tuning the dust emission factor from 0.7 to 0.3 and the CESO emission factor from 1 to 1.45. So both emission factor tuning is increase the emission of the dust and the CESO, and we achieve the goal is in the model results, our dust AOD is between MAM4 and MAM5 is the same, and also our total aerosol AOD between MAM5 and MAM4 is the same. And we have 2 sets of simulations. One is the historical simulation, is between 1980 to 1997. Second is a 2000 climatology simulation. Let's see the results. This is from historical simulation. And we compare MAM5 and MAM4 with the observational data. This is the sulfate aerosol burden only in the stratosphere from 1981 to the 1996. So we can see the MAM5 is reproduced almost the same burden of the sulfate in the stratosphere after the volcano eruptions and match the observation as well as MAM4. Also, we check at 2 different sites. At 2 different sites, the stratosphere AOD compared to the 2 LIDAR observations. One is at the middle latitude, one is in the tropics. So both can match the observation very well. And we can see MAM5 and MAM4 almost identical in reproduce the stratosphere AOD. Okay, that's our first purpose. Then we look at the zonal mean of the sulfate aerosol first. This is zonal mean after Pinatubo eruption. So this is the 1991 to 1993 3-year average. The first row of the first column shows the MAM4 results. For MAM4, sulfate aerosol concentration. Sum up all the modes, and here show MAM4 only in the coarse mode. In the right side, we show the MAM5 all modes sulfate aerosol concentration, and the MAM5 sulfate aerosol concentration only in stratosphere sulfate modes. We can see MAM5 reproduces the sulfate aerosol burden, not only in total amount, but also in the distribution. And our designed sulfate stratosphere sulfate mode 5, will reproduce the burden as the coarse mode in the stratosphere. And we have very little impact in the troposphere for the mode 5. Here we check the impact of on the dust. We see the dust. This is almost burden from MAM4, almost concentration zonal mean from MAM5. We see the because MAM5 will have a higher standard deviation, is 1.8 compared 1.2, and also without the renaming process from the accumulation to the coarse mode for the dust. We can see the MAM5, even we largely increase the emission, we still reduce the dust burden, especially along the tropopause area in both high latitudes. You can see this comparison. And
only 2 minutes left. Okay.
Oh, sorry. Yeah. So here we show the seesaw. The same thing, we can reduce this aerosol concentration around the tropopause, because this high aerosol concentration around tropopause is not physically reasonable. Then we check the radiation curve and also the cloud impact. So this is the difference between our MAM5 and the MAM4 results. And is from south, zonal mean from south to the north. We can see this is at the top of the model, FSNT minus FLNT, that is the residual of the radiation. So the MAM5 generally can reduce the radiation almost all the latitudes, especially in the North Pole and the south middle latitudes, because here the emission increase largely. And we can see almost identical impacts on the shortwave cloud forcing. This shortwave cloud forcing we attribute to the change of the IMP and the ice water pass and the liquid water pass. We can see our ice water pass largely decreased in the south and the north high latitudes. In the opposite direction, we increase the liquid water pass in the south and the most high latitudes. That causes this change. And yeah, I think I'm out of time. I will go to our conclusion. It's by adding this stratosphere sulfate aerosol, MAM5 can reproduce the sulfate burden in the stratosphere. And in the troposphere, our impact is limited and is more likely to impact on the dust. Yeah, That's all. Thank you.
Okay, thank you. And any quick questions for Zimin? And this one question from Yunqian, and she asked a very nice talk. Zimin, I have a question regarding the stratosphere sulfate. What is the purpose to adding additional sulfate cosmos if MEM5 is reproducing the MEM3 results?
Okay, yeah, thank you, Yunqian. It's a very nice question. So the purpose we add is first we have to simulate for WACCM we have to simulate the stratosphere sulfate. But if we add them together, to keep the sulfate burden, we have to reduce the STD of the other coarse aerosols, coarse mode aerosols, as we shown here, the other coarse mode aerosols. And by changing the STD for other coarse mode aerosols, we will make some the negative effect for the dust, especially for the dust. That is reported by the Wu and Li in the recent 2020 paper, and also reported by the Natalis dust group under our private conversation. So we bring back the 1.8 standard deviation coarse mode and to make the troposphere aerosol distribution better.
Okay, let's move on. So we run out of time. And the next talk is given by Hunter Brown. He's going to talk about the biomass burning aerosol in the CAM model. Hunter,
all right.
Are you ready?
Yeah.
To me, there's another question, so you can answer in the chat. Okay.
Sure, thank you.
All right, can everyone see that?
Yes.
Okay. Great. Thanks, Xiaohong, and excited to talk to everybody here about some research I've been working on over the last couple years. Again, my name is Hunter Brown. I'm a postdoc working at Texas A&M with Xiaohong Liu. And my talk today will be discussing biomass burning aerosol optical properties in a variety of Earth system models and chemical transport models. But today I'll just be talking to you about findings in CAM. Many people helped me with this study. I don't have enough time to acknowledge them all, but I've included a reference to our paper that discusses this research if you're interested. All right, so a little introduction to biomass burning aerosols. Biomass burning is responsible for a majority of global combustion aerosol, which includes fossil fuels and biofuels. I'm showing here the global fire emission data set, biomass burning emissions, mainly just to bring your attention to the main emission sources. So the main source for biomass burning aerosol is Southern Africa, followed by South America, Southeastern Asia, and then boreal forests. The composition for this smoke can be broken down into a few main components. We have primary aerosols that are directly emitted from these fires, and that includes the strongly absorbing black carbon or soot, as well as organic aerosols, which can be both strongly scattering as well as absorbing. And then you can get secondary aerosol formation from gas phase emissions. The climate impacts of biomass burning smoke are quite complex, and I just have a couple pictures to show to kind of bring that point home. We have a fire from Santa Cruz, California, and you can see the smoke is very, very bright. It's strongly scattering, and we can contrast that with a bushfire from Australia, which is very dark and strongly absorbing. So depending on the fuels that are burning and the regions from which these fires are originating, you can have very different climate impacts. So the basis for this study was work done by Rudra Pokhrel, a colleague from University of Wyoming, And his work looked at biomass burning laboratory studies where he compared single scattering albedo at visible wavelengths of light to black carbon to total carbon ratio for a variety of global fuels. So we're looking at this comparison, and what it tells you is that smoke is more absorbing when you have a higher black carbon content in your smoke, and vice versa. When you have more organics, your single scattering albedo tends to be higher, and so the absorption of the smoke is lower. And we settled on this as a pretty good model comparison because it's not dependent on resolution. We're looking at two intensive properties and allows comparison between models of different resolution and also observations. And it not only validates model optics by looking at single scattering albedo, but also how well the model is simulating carbonaceous emissions. Before we compare models in this framework, we also compiled 12 other global field and laboratory studies to make sure that the behavior that was shown in Rudra's work held true for a variety of different campaigns. We have observations from North America, South America, Southern Africa, and then a couple from Indonesia and India. And we overplotted those here in these two figures. The left is showing single scattering albedo at green wavelengths of light. The right shows single scattering albedo at red wavelengths of light. But all of these observations are isolated instances of biomass burning influence measurements and establishes this as a reasonable assumption for biomass burning fuels. So that then raises the question, how does the community atmosphere model perform in this comparison? And from here on out, I will be taking the parameterization from this left-hand model as a comparison to version 5.4 of CAM. So same plot as before. Observations now are plotted in gray with the best fit in this gray line here. The model data from CAM 5.4 is these colored crosses, and the solid blue line is the best fit to this model data. Different colors represent different regions of biomass burning emission, where red corresponds to Africa, orange, South America, etc. And we also do the same with observations by showing the average observations from Africa with a spread denoted by this bar. But I won't be getting too much into that, and we'll be focusing more on the single scattering albedo comparison on the y-axis here. So the first thing we see is that the model reports higher absorption than observations, a lower single scattering albedo. And this is especially true in these larger contributors to biomass burning aerosol, Africa and South America. In comparing the model to observations in this framework, we had to isolate grid cells that were influenced by biomass burning emissions. And the strategy that we used to do that resulted in most of our model grid cells being dominated by fresh biomass burning emissions, which in the aerosol treatment, which is the modal aerosol module, is the primary carbon mode, so mode 4. So this gave us a place to start in terms of understanding why the model was more absorbing than observations. But we also need to understand kind of the mechanisms in this model that would lead to this disagreement. So models calculate aerosol optics using me theory, and this just describes absorption and scattering of electromagnetic radiation by homogeneous spheres. So with that gives us kind of three main causes, three main mechanisms that might be explaining why the model is more absorbing than observations. The first is particle composition. So if your biomass burning aerosols are lighter, more scattering, say the more organics versus your more absorbing black carbon aerosol, you're going to affect light absorption in biomass burning smoke. In the size range of interest with biomass burning aerosols, and when we're looking at visible wavelengths of light, particle size also plays a role, where larger biomass burning particles are going to scatter more. They're going to have a higher SSA than these smaller particles. And lastly, particle mixtures also contribute, where if you were to treat all of the species, all the components in biomass burning emissions as individual aerosol particles, it would be less absorbing than if you assumed some internally mixed treatment. And these internally mixed treatments and models can go anywhere from randomly oriented, black carbon absorbing cores in a scattering coating, or core shell treatment where you have this perfectly centered black carbon core, or as CAM treats it, a volume mixing assumption, where the model will volume weight the refractive indices in each grid cell and create this idealized blended together aerosol. And of the internal mixed treatments, this volume mixing assumption tends to be more absorbing or report more of an absorption enhancement compared to external mixtures than the others. So sorry, before I go on, I'm not going to go into detail regarding the changes we made, but we approached this study by running sensitivity experiments where we either treated our biomass burning aerosols as externally mixed, we increased the particle size, or we reduce the absorption to affect particle composition. And so this is looking at those sensitivity tests plotted on the same figure I had shown before. And all of our changes actually improve our model agreement with observations. Blue is our default simulation. Red is a simulation where we made biomass burning black carbon less absorbing. Gold is looking at simulation where we increase biomass burning aerosol size. And then maroon is treating biomass burning aerosols as externally mixed. And pink is all three of those changes in one simulation. So the largest improvement we saw was assuming that these aerosols are externally mixed. And while this isn't a realistic assumption, as observations show that in reality these particles are internally mixed, it seems to be a better assumption than the internal mixtures that are being assumed in CAM currently. So now, towards the end of the talk here, the last thing I'll talk about is what are the effects on TOA flux with these changes. So we look at the direct radiative effect, or the change in TOA flux with aerosol radiation interactions due to these changing biomass burning properties. In the default model, in CAM 5.4, you get a slight atmospheric warming due to biomass burning aerosols, and this is largely driven by this transport over the South African cloud deck. When we implement all the changes I showed previously, we actually go from slightly warming to a global average direct radiative effect that is slightly cooling. And if we look at the difference between the two, it's about a 0.07 watt per meter squared difference. And that's really centered, the majority of that change is over the South African cloud deck. So big implications for different climate impacts. We didn't try and quantify them in this study, but I think it's important to understand that part of what we're doing is we're changing aerosol size. So this has really large implications for cloud radiative effects. Also, CAM wasn't the only model that showed this underestimation in single scatter albedo. And so this might be kind of a systemic problem amongst other Earth system and chemical transport models. So yeah, just to summarize, model simulations in this comparison tended to report lower biomass burning single scattering albedo than observations, but we were able to improve this comparison with changes to composition size and mixing state. And as CAM went from slightly warming to slightly cooling in its biomass burning direct radiative effect, this may have implications for other models if they're changed similarly for estimates in these model ensemble calculations. All right, thanks. With that, I'll stop.
Okay, thanks, Hunter. And yeah, if you have a question, just post that in the chat. So I see there's one question from Pablo, and he's asking, can there be an effect from of the particle shape? Consider that BC is usually not spheric, and I would think that it may apply to brown carbon as well. Yeah. So.
Pablo, I don't really know if there are efforts to implement shape changes in the ME calculations. I think that would have an impact, but I can't say.
Okay. Other questions? If not, let's move on and to the next talk. Thank you, Hunter. And given by Kan-Min Fang from MIT is going to talk about exploring the natural aerosol from DMS oxidation and implication for the aerosol forcing. Hunter, could you unshare your screen? Hunter, could you
I don't think I'm sharing anymore.
Okay, so see the Kan-Min, could you share your screen?
Yeah, sure.
Okay.
So can you all see my screen here?
Yes.
Oh, great. So thank you so much for giving me this opportunity to present our work here. And so my name is Kan-Min Fang. I'm now a postdoc at MIT. So today I'm going to talk about my project with colleague Hugh in exploring the natural aerosol formation from DMS oxidation and implications for aerosol forcing. Before I go into the details, I would like to thank all the colleagues at MIT and Anchor for their support and inputs to this project. So showing here is the popular IPCC radiative forcing chart for various climate change drivers. And this bar here showing that is showing the sulfate direct radiation effect, which underlies scattering and absorption of incoming radiation by the atmospheric sulfate aerosol. And this bar here is indicating the indirect effect of the aerosol, which underlying how cloud adjusts to increase or decrease in aerosol loading. And one specific thing that I want you to focus is that these two numbers that is estimated by IPCC are quite uncertain. And this uncertainty can be attributable to not only how good or bad we are simulating the atmosphere under the current conditions, but it is all the uncertainty also comes from how good or bad we are working on. We're estimating the pre-industrial atmosphere, the baseline. So actually, like a previous study has already shown that the uncertainty in determining the aerosol indirect radiative effect is attributable to the combined uncertainty of both present day and pre-industrial sulfate burdens. The other study also showed that because of the logarithmic response of CCN concentration to anthropogenic emissions, the cloud drop concentration to the CCN concentration and cloud albedo to cloud drop concentration, the net effect is that the aerosol indirect forcing is more sensitive to the to the uncertainty in aerosol burden in a cleaner, pristine atmosphere, such as in the pre-industrial era or in a remote marine atmosphere. That's why we are focusing on DMS chemistry in this project. So DMS dimethyl sulfide, was the main predictor or precursor of sulfate aerosol, and it is still a primary one. So from here you can see the DMS emission was quite substantial in the pre-industrial era, even though it is outcompeted by anthropogenic SO2 in the present day conditions. DMS emission is still contributing to around 20% of all atmospheric sulfur sources. And it is still the single largest contributor of sulfate precursor over the remote marine atmosphere. All of these has motivated us at MIT to expand the DMS chemistry in CAM-chem in order to better represent the impact of DMS oxidation on sulfate formation over this region and the aerosol forcing in the pristine environment. So our model development work focus on expanding the chemistry scheme in CAM-chem that is based on the TS1 scheme. And this scheme can be summarized in this simple graph network. Each vertex in this network represents the chemical or a species, and each edge here denotes a reaction. A thicker edge indicate a reaction with larger annual and global reaction rate. And the red edge here are indicating of gas phase reactions. The green edge here indicate a aqueous phase reaction in the interstitial aerosol particles, and the blue here indicate cloud chemistry. So compared, like other global models, the TS1 scheme used a rather simplified DMS oxidation scheme that directly convert DMS into SO2 and sulfate. In our new scheme here, we keep this major pathway, but on top of that, we are also adding 44 new reactions that is based on various lab and field studies. And these new additions allow the model to simulate some key intermediates that is produced during DMS oxidation, including HPM, TF, and MSA. And these long-lived intermediates are actually observed in various field studies. And the model is also now capable of capturing some faster pathway, such as these aqueous phase reactions. Now I'm showing you some of our preliminary results. We found that with the new chemistry, if we are assuming all these species as the terminating species, we can calculate a product bunch ratio like this. And here I'm showing you in this percentage, like 31% of total DMS loss due to the new chemistry will result in the formation of HPM-TF, and 21% will be MSA. And this is the spatial distribution and how important each of the portion of the yield being produced locally by the DMS oxidation. And one immediate consequence of this extended chemistry can be summarized here by these two bars, which showing you the annual mean global burden. We see that by comparing the standard simulation here, we using the standard chemistry and the present day emission versus the run with the modified chemistry with the present day emissions, we found that first observation is that the DMS burden encapsulated here is now, some of them is directed to MSA and HPM-TF, and we are also seeing a net increase in sulfate burden, which combining the two effects makes the total atmospheric sulfur burden increased. And we are also seeing that the lifetime of DMS is decreased because now there are more DMS loss pathways, and also the two intermediates that we are showing here, they both have substantial lifetime, which would allow them to be transported to a larger range from the DMS emission source, and could result in a wider spread of sulfate formation over the remote regions. Before we look into the aerosol forcing analysis, it is important for us to conduct a reality test. So we are comparing our model simulations with multiple sets of measurements. We first look into DMS. Here I'm showing you a map. We're using two sets of measurements here. The first one is those circular dots that is enclosed by these green simplex, and they're acquired by the ATOM measurement that is done by NASA, which is a global aircraft measurement campaign from 2016 to 2018 over 4 seasons. We group these observations from ATOM into 3 regions for easier comparison, and we extract the model results that has matching lat altitude and also month to compare with the available measurements here. And one simple conclusion that we can draw here is that it seems like our model is doing okay over Pacific and the Atlantic with a slight overestimation. But when we point to the Southern Ocean, we found that even though the new chemistry that we add in the model can somehow reduce the overestimation or the high bias of the model, but our model result is still quite a lot more than what has been seen by ATOM. And we are also comparing our model result with another set of measurement, which is acquired by the Focal Rex campaign, which is a campaign combining the flight measurement and also ship-based measurement. And we are seeing one observation is that this measurement they report higher DMS values over this area, the blue box here, and compared to them, we're doing okay. So the other thing that we want to check is the MSA to non-seasonal sulfate ratio, which is an indicator of how important the biogenic emissions of sulfate over the remote region is. And it is not surprised that we are seeing high MSA to non-seasonal sulfate values over the remote area here, which is where natural aerosol become more important. And when we are comparing to a campaign that is happening here, which is called CESM, and we found that our sulfate is doing okay with the observations, but the MSA is quite off. We are having a strong low bias. And comparing to ATOM again, so we're also seeing the performance of sulfate model values are okay compared to, and we're also doing okay in terms of MSA in Pacific and Atlantic, but we are again overestimating in the Southern region. So because we're seeing some consistent mismatch in the Southern region, we suspect that it is related to the uncertainty in DMS emission, and this is something that we are still working on to improve the high bias. And now, one encouraging thing is that it seems like our model sulfate is still looking okay when compared to the observations. So now we dive into the analysis of the aerosol direct radiative effect. This plot here shows the zonal mean of sulfate burden obtained from 4 simulations. The red ones are the one with the new chemistry. The black ones are the one that with the standard or the model default chemistry. And the dotted line here are simulations with P-industrial emissions values. And as expected, we are seeing the increase in sulfate burden is much higher with respect to emission when comparing the solid lines and the dotted lines. And the chemical changes, the sulfate burden change induced by chemical change, which is the distance between the red and the black lines are not that substantial compared to the emission effect. And we're also seeing that the model DRE, which is calculated the derivative effect, has stronger negative correlation with sulfate burden by seeing how similar these two patterns are. And I'm showing here the annual global means that's calculated by the two simulations and comparing that with other previous publications. We found that the new chemistry has improved the estimation of global mean DRE. And it seems like the simulation with the new chemistry has a closer value to other previous previous studies. And when we try to focus more on the marine atmosphere, we we remove all those land contribution to sulfate DRE and sulfate burden. We are seeing a similar effect, meaning that the chemistry didn't affect that much over the marine region when comparing to the land, or the chemical effect is consistent over land and over the marine. And the next focus of our study is that we were interested in seeing the aerosol interact effect. And this is where the story becomes more interesting. Here, I'm showing you the solar mean of sulfate burden again over the marine atmosphere versus these marine-only salt wave cloud forcing. We found that it seems like the spatial variability of the two are not quite correlated. And following some of the previous study by the CAM-chem community, we are also exploring these other variables that is related to the cloud properties, including cloud cloughage, liquid water path, and also column cloud drop number. We found that it seems like the spatial variability of cloud forcing is more has a strong correlation with them. And so to verify that, we extract. So we extract the grid cell. We extract the variable at the grid cell where we find statistical significant difference between of the sulfate cloud forcing between the simulation with the standard model and our modified chemistry. And this part I'm showing the change in the correlation, the linear regression analysis of the change in sulfate cloud forcing versus the change of the cloud cloughage fraction and the liquid water path and cloud drops, and also sulfate. We found that even though the pattern is similar, the numbers are similar, we found that all four variables would have a stronger correlation with the change in cloud forcing when it is under the pre-industrial emissions. So, which can be concluded that a strong correlation between the change in forcing and change in sulfate burden induced by the new chemistry is witnessed more strongly in the pre-industrial conditions than the PD conditions. Here's my concluding slide. We found that I would like to conclude that by showing you by mentioning this metric. So when we are comparing the change in DRE or change in cloud forcing, and when we divide it by the change in sulfate, we found that under the present day conditions, this effect of the new chemistry on these numbers are not that significant comparing to the pre-industrial region, the pre-industrial conditions. So in conclusion, I would say that in this study, we found that disproportionate radiative effect or radiative forcing sensitivity to sulfate burden induced by new chemistry under different emission conditions. So here, this is the end of my my presentation here. In this study, we implement new chemistry there, and then we found that this new chemistry has led to a substantial change in sulfate burden, and that has a consequence in the change in sulfate DRE and sulfate indirect effect. Thank you so much.
Thank you, Kunming. And there's one question in the chat. Are the oxidants the same in pre-industrial and the present day simulations?
sorry, I lost condition. I mean, I lost connection. Would you mind to repeat the question?
Are the oxidants the same between the print ultra and present day simulations? Are they the same oxidants?
Oh, we keep all we keep all natural we keep all greenhouse gases, and also so anything that can be prescribed except from the anthropogenic emissions keep constant at 2000 level.
Okay, there's another question. We have to move on. Maybe you can reply in the chat. And
yeah, sure.
Thank you. And that's the last talk in the aerosol session is given by Sarah Hancock from Columbia University. And she is going to talk about the changing PM 2.5 and the related metrology over India from 1950 to 2014. Okay, hi.
Hello, can y'all see my screen okay?
Yes.
Okay, well, hi everyone. My name's Sarah. I'm an undergraduate senior at Columbia University, and thank you for taking the time to hear about our research. I've been working with Dr. Arlene Fiore and Dr. Dan Westervelt on research about meteorology and PM 2.5 in India using a 12-member ensemble from CESM to WACCM 6, and that's what I'll be discussing today. In recent years, India has had extremely high PM 2.5 levels. This video is from a news article from last year that shows the poor air quality in New Delhi. And we want to better understand how meteorology might be influencing these pollution levels. But something that makes this difficult is that India lacks long-term observations for PM 2.5. So what's new about this research is we're using CESM2 coupled with WACCM 6, which has full atmospheric chemistry in the troposphere and stratosphere. We currently have 12 ensemble members, which means that for each member, the model ingests the same greenhouse gases and air pollutant emissions, but starts with different initial conditions, such as slightly different atmospheric states in 1950, and it's run through 2014. What this gives us is 12 different possible scenarios of what the climate system could have looked like during this period. And the reason why this is useful is that any variation between the ensemble members is an indication of climate variability, while any trends that occur across all of the ensemble members indicate anthropogenic forcing. So essentially, even though we don't have historical observations for PM 2.5 in India, these simulations give us a range of possible estimates of what the atmosphere could have looked like all the way back to 1950 that we can use to look at both the role of climate variability and of anthropogenic forcing. Prior research from Jordan Schnell looked at meteorology and PM 2.5 over northern India in more recent years. And they found that the factors that led to higher PM 2.5 concentrations were those listed here, like low boundary layer height. And most of these factors are related to the stability of the atmosphere. So the idea is that a more stable atmosphere allows for more PM 2.5 buildup at the surface. So we chose to look at the same meteorological indicators using the 12 WACCM 6 ensemble members. I wanted to first show this plot to better explain the significance of the different ensemble members and the variation between them. So each row of this plot is a different meteorological variable. And what we did is in each grid cell over India for each ensemble member, we took the difference between the value of that variable in 2014 and the value in 1950. Then we plotted the ensemble member with the minimum, median, and maximum changes in each grid cell, which are represented by the different columns. So basically, each plot is showing how much each variable changed over time, and the columns show how this change varies between the ensemble members. So if we zoom in on the fourth row, that's relative humidity, you can see that there's clearly variation between the ensemble members. So for the median plot, most grid cells over India see a slight increase in relative humidity over time. But if you look at the right and the left plots, the extent of this increase is different between the ensemble members. So there's a fair amount of variation there. This is very different from the third row of this plot, which is surface PM 2.5. You can see that the patterns of increase in PM 2.5 are really similar in all of the plots. You're always seeing this maximum increase in the northern part of India. So essentially, we're seeing that even with variation in meteorology, there's a large increase in PM 2.5 in all the scenarios. To build on that idea, we looked at trends in the grid cells encompassing 5 different cities. So these plots are showing surface PM 2.5 from 1950 to 2014 in each city. And there's one line plotted for each ensemble member. So you can see there's some variation between the ensemble members, but there's a clear trend that PM is increasing in all of the cities. In some cases, like in New Delhi, you can see PM concentrations are almost tripling from 1950 to 2014. We also looked at the seasonal cycles of PM in the same cities, and this plot shows the cycles by decade. So the blue line at the bottom of each plot is the cycle from 1950 to 1960, and the shading represents the range of the ensemble members. And what we can see from these plots is that the seasonal cycles of PM completely shift from the 1950s to 2014. If you look at New Delhi, for example, the initial seasonal cycle has a small summertime peak, but as time progresses, the wintertime peak increases more and more, so that by the 2010s, we're seeing a higher wintertime peak than in summer. This is what we expected because wintertime emissions in India have increased since the 1950s, but this again shows that this increase happens no matter what variation there is in the meteorology. We also looked at correlations between PM 2.5 and meteorology, and what we found is that correlations are different between cities and seasons, and they change over time. So I won't go into all the different correlations, but I'll show an example of what I mean with New Delhi and Kolkata. This plot shows the annual correlations for relative humidity and inversion in February through May from 1950 to 2014. And when I say annual correlation, I mean that we use the daily values of PM and meteorology from just the months of February through May from each year and calculated the correlation coefficient using those values. And then we plotted this correlation each year. So the blue line is New Delhi and the orange is Kolkata. And you can see just by glancing at the plots that the trends are different, especially with inversion, which is that bottom plot. With inversion throughout the whole time period, New Delhi has a pretty low correlation. Maybe it's slightly increasing, but in Kolkata, the correlation starts off high, close to 0.8, and decreases to almost 0 by 2014. So to show why this might be happening, we can look at this scatter plot showing the relationship for Kolkata in 1950. There's a pretty clear linear relationship between inversion on the x-axis and PM on the y-axis. But if we include values from 2014 on the same scale, there are just so many high PM values at all inversion levels that you can't see the same relationship anymore. So far, all I've shown are model simulations, which of course begs the question, how good is this ensemble at representing the real atmosphere? And as you all probably know, the model isn't meant to capture the exact weather on a given day, but we do expect it to be able to capture something like the seasonal cycle of PM, and that's what we're looking at here. So this plot shows the last few years of model simulations, 2012 to 2014, with US consulate and embassy observations from 2013 to 2015. And the first thing you might notice is that the model really underestimates PM concentrations. The model is shown in red and the observations are in black. And if you look in New Delhi in January, for example, the observations are above 200 micrograms per meter cubed, and the model is below 100. The other thing is with the model, we see this summertime bump in a few cities that's not consistent with observations, especially in Mumbai, you can see it really clearly. We did look at the components of PM individually, and it seems like this could be because the model is overestimating natural sources like dust and sea salt. It's also worth noting, though, that this is a coarse resolution model, so the values from the model are taken from a 1 degree by 1 degree grid cell, whereas the observations are point observations from US consulates. We also looked at aerosol optical depth using the Aqua and Terra satellites. This is the average monthly AOD at 550 nanometers over the years 2003 to 2014. And with these plots, we also see a shift in seasonal cycle, where the peak AOD comes about a month after the peak observed by satellites, especially with New Delhi and Mumbai. So to figure out why the seasonal cycles of PM and AOD might be shifted, we wanted to see if maybe the timing of the monsoon was off, since that would impact both PM and AOD. So we plotted seasonal cycles of precipitation from 1979 to 2014 using precipitation data from GPCP. And in many of the cities we looked at, the precipitation seasonal cycle over India is also shifted. In Mumbai, for example, the observed month of maximum precipitation is in July, but for the model, it's 1 month later in August. And it turns out that in the model, the shift is present across most of India. These two plots show the month of maximum precipitation in each grid cell, and the left plot is the observations. And for most of India, the month with the most precipitation is July. But for this ensemble, which is this plot on the right, the months are August and September, so 1 to 2 months later than observed. So this shift in the precipitation and monsoon timing is a good explanation for why the summertime bump appears in the model, because if there's less precipitation in June and July, that allows for a PM 2.5 buildup during these months that wouldn't occur in the observations. And this also makes sense with the AOD seasonal cycles, since it's been suggested that the maximum AOD in India occurs during the monsoon from dust transport. So if the monsoon timing was later, then the peak AOD would be later as well. Something that's interesting about this shift, though, is that it doesn't seem to be present in simulations from CESM without WACCM 6. So this top figure is from a paper by Gerard Miele, and it shows that for CESM2, the month of maximum precipitation across most of India is July, which matches the observations, but this isn't true of the ensemble we're using with WACCM 6 included, which you can see in the same plots I showed earlier. So overall, we found this mystery in precipitation and monsoon timing, and our next steps will probably include looking into that further. But just to circle back to the plots from earlier, the main takeaway from this project is that in all the ensemble members, PM increases in India no matter what variation there is in the meteorology, which corroborates the dominant role of air pollution emissions on poor air quality in India. Thanks for listening, and I'm happy to take any questions or comments if there's time.
Thank you, Sarah. And any questions? And you can put that in the chat. Let me see. And so this one question already asked, already be answered, but I can let you know. Is there any reason why you are using the CESM2 WACCM 6 with a high top instead of CAM-chem low top? Yeah.
Yeah, I see Arlene already answered in the chat that the ensemble was available via another project. Thanks, Arlene.
And before, I have another question. So are these simulations driven by the observed meteorology or just nudged meteorology or free run simulations?
Sorry, I think it cut out for a second. Could you repeat that?
I mean, are these simulations, are they free run meteorology or they are just nudged meteorology? So are they free run or just nudged, like the meteorology field are nudged?
I'm not sure. So I think free running,
Okay.
but yeah, I'm not totally sure.
Okay, this I think the answer to that is fully coupled. Yeah. Okay. So if it's fully covered, that means the aerosol climate or aerosol meteorology could have interactions like this. If you have like aerosol perturb the meteorology, and meteorology could have feedback on the aerosol. That is, the interaction could be include that in the model. Okay, thank you, and thank you, Sarah. Yeah, for a nice talk. And this conclude our aerosol session. So we have, I think, I don't know, Julio, how long we are going to talk about. We have discussion on the cloud and the aerosols.
Right.
So,
we have a discussion scheduled for you know, kind of a part 2 of the clouds. Now we have the aerosol.
yeah.
We're a little late. I think we might, you know, have a shorter discussion, but I think we should open it up for comments on physics in general. I'd say let's see if there's any, you know, are there any immediate things people want to bring up? I have some questions that I'll post in a second if nobody has anything they want to talk about, but let's give people a chance. Yeah, I'd say let's go till, I don't know, let's go another 15, 20 minutes.
Yeah, I think yeah, reasonable.
Well, there's another question for relating to Sarah's talk.
He's asking, Aline is asking if anyone has any insight as to the delayed monsoon onset of India in the CSM2 WACCM 6 that Sarah showed. And is there any delayed? Is that, Aline, do you mean that the model could end simulated the monsoon onset or in the summer? That maybe
Yeah,
yeah.
maybe sorry. Hi everyone. Yeah, I was just curious if anyone else has seen this, where the precipitation seems to be delayed by about a month compared to what seems to be in the observations.
So this is Rich. What kind of data are you using? Are you using the time series files or the H0 files? Do you recall from CAM?
Oh, from
Yeah.
Oh,
Because there
actually,
is
go ahead.
Well, we can talk about it offline, but there is
Okay.
a catch you out month time stamping issue with the way that the raw H0 files are done. So you're off by a month in certain circumstances, but we can talk offline.
Okay, that would be super helpful.
Sure.
Thank you.
Okay. Why don't I'll share my screen. I have a few questions on physics. Might spark some discussion, maybe not. I'll just share them and we'll see. Is that okay there, Xiaohong?
Yeah, go ahead.
Okay. Do you see 4 questions or 4 issues?
Right.
Okay, so these are things that came up in my mind during yesterday and today. It struck me that, you know, we heard lots of in the last session we heard a bunch of talks on aerosol physics, and it strikes me that our at least our local development activity really is sort of focused right now on what I would call macro physics. You know, we're really exploring convective, you know, unified convection in club EDMF. We're exploring momentum transport in club. Rich is leading you know, he's leading the PBL activity, and in AMP, which really is, I would characterize it as more in the macro physics direction. I would also say that about the land surface physics coupling talk we heard yesterday. We also heard, about time step sensitivity. There's vertical resolution sensitivity, which we know is in the model. I don't think anybody emphasized it to this time. There are also tools for exploration, including the radiative convective equilibrium. Chris Cruzy showed results from nudging. I think we're in the process of trying to maybe make those nudging analyses a little more rigorous. And there's the usual, single column. How useful are single column studies in general for evaluating physics? And the issue came up. I think it was after most people had signed off. But there's there's some interesting possibilities we have, especially with the SE dicore, of coupling physics and dynamics on different grids. In particular, we can couple. It's easy for us and kind of economical to couple physics on a coarser grid than the dynamics is running. So, for example, the dynamics is essentially running with more or less 9 control volumes per, or maybe more. I'll let Peter correct me if I'm wrong, but in practice, about 9 degrees of freedom in each spectral element, whereas there's some evidence we can get pretty similar solutions if we restrict the physics grid to 4 degrees, so a 2x2 physics grid inside each spectral element. So that's a possibility. So those are things that came up for me, and I'm happy to discuss any of these or let other people chime in with their own questions and comments. But
yeah, Julio, we could add something related to the aerosol, like the aerosol direct indirect effect in the CAM. Yeah, so there are talks about the direct indirect effect in the model, or how that relate to the aerosol process, like the oxidation aerosol process, like chemical reaction and the emission change.
And along those lines, I'll add.
It's microphysics, yeah.
Yeah, so we'll see tomorrow that does seem to play a role, or it might be playing a role in our climate sensitivity being so high. So anyway, these are some possible. These are things I'd like to address at some point. We can either address them now, or we will also have more discussion tomorrow. But anyway, so I'll leave these up, but people should feel free to chime in with whatever they want to talk about.
Yeah, you can put that. You can put your comments in the chat, or you can speak out. Which way you like, whatever you like.
If no one is going to say anything, I'll say that I'm not sure that we've been spending most of our time in the macro physics, in the sense that I get the feeling that Andrew has a really robust microphysics effort going on right now. It's just that it's
that's true.
Talked about it so much.
Yeah.
And I'd also like to add that I think that convective microphysics in particular is something that I'd like to not fall off the table.
Mm-hmm.
Yeah, we have in the model a configuration with the convective microphysics done by Song and Zhang but that is not, it's just an option, not in the default model. But that with convective microphysics could affect on the radiation balance, but I don't know how good is that. We probably need to tune the model or something if we want to include the convective microphysics.
I think that there just hasn't been a big driving force in the meetings where we decide what we're going to put on the trunk for turning that on. And I think part of it is because, yeah, when you do turn it on, you end up having a lot more detrained condensate. And so it would require a lot of tuning.
Right.
And so I think it's just complacency, basically, that we haven't done it. And maybe a lack of enthusiasm to enhance the ZM scheme when a lot of people have an eye towards the future and potentially having a different convection scheme. So those are just my observations of why it hasn't been turned on yet, even though it's as simple as a nameless change.
Could I just follow up? This is Leo. This topic actually has come up, but yeah, not with a strong push. I would second, though, what Peter was saying. There really is a very severe inconsistency in the level of the microphysics between convection and the stratiform macrophysics. And convection is really a major source for the stratiform clouds. There is published work on that version that Song developed, and it actually shows some nice improvements in the simulation quality. I'm not sure how difficult the tuning would be. Of course, you know, inevitably a paper like that's a little selective in terms of what it showed, but I took it to be actually quite promising. I'm not sure it would be that difficult to tune it. And I would at least recommend, you know, taking a close look at this and seeing how feasible it is. It's really critical for doing aerosol cloud interaction problems because a lot takes place. Convective invigoration, there's a whole set of things that tie to this. I know there's always a question, will we stay with CM? But, you know, this code does exist. It may not take that much to do this. So I recommend a harder look at this. It could be a high gain for low investment opportunity.
And I would expect, Adam can correct me, but I think Zhang's approach to convective microphysics might be sort of grafted into the club EDMF plume model.
You mean the default simple microphysics?
No, the more complicated microphysics in Song and Zhang, that might serve as a model for what we do in the MF plumes.
Right, yeah, that is, I think we've established as a target. You know, I think too, when we do these dicore comparisons, we're gonna have to do significant retuning anyways. And the opportunity to, you know, instead of messing with all these club parameters, let's turn on the ZM microphysics and see if that doesn't help our TOA problems as well. So,
yeah. Now, I believe the microphysics in there is essentially, it's a somewhat earlier version of Morrison Gettleman that's in the Song Zhang work. So it would begin to render the microphysics in the convection much more consistent with stratiform. This is an issue that almost all GCM groups have had. I would honestly say over decades, people have brought up at international meetings that the need to make the microphysics in convection more consistent with the stratiform. So here's an opportunity actually where I think some leadership could be shown. And I think Adam's idea is good. If we're going to have to do retuning anyway, maybe it would be good to sort of start out with this. Maybe, you know, a few quick runs to see if we're reproducing what the Song Zhang paper was showing. But my recollection is they had some nice improvements vis-a-vis observations in that work. So it looks like a lot of gain with maybe minimal pain.
Yeah, I want to add that yeah, my group students she also further improved Song and Zhang convective microphysics, and she implement like the settling for the snow and ice is more consistent with observation. The settling velocity of the snow ice in the convection. Yeah, so we are going to have a paper published soon, and that is we further improve the Song and Zhang convective microphysics. And another comment is and we could consider as Leon mentioned that all that convective microphysics could in fact on aerosol, because the aerosol like the scavenging and the transport in the convection, a major player for the aerosol vertical distribution. That we should make it more consistent with the aerosol convection interactions.
I see Brian Medeiros had his hand up. I don't know if he might have taken it down.
I took it down, but I was just going to say, I think I have this recollection that Andrew said that the convective microphysics that was implemented by Song et al. was what Leo said, an older version of MG, and it might be difficult to run two versions of MG simultaneously. So it might be harder to run that configuration with the newer versions of CAM than we think, but I'm not sure.
Okay.
I know it runs with CAM6, but are you saying whether there might be introducing inconsistencies, even though it does run stably?
Yeah, and there could be. I don't know. I just have this recollection that of some. I thought it was Andrew, but it could have even been Brian Eaton, warning us that it wasn't as easy as we thought it was.
So it might involve some updating of what's in Song and Zhang.
Yeah, maybe, or maybe just testing to make sure that we're running what we think we're running.
Isn't the problem that it's all diagnostic with ZM and it had to pass to be prognostic diagnostic back and forth? That was my recollection into MG.
Yeah, Julio, you could add that consistency with aerosol process in there.
Yeah, so I think that as I think that it's running. I mean, well, that paper is, I guess, a few years back now. I've forgotten exactly when this was published. But they're scientifically, I'm sure they're not quite consistent anymore. Although if you were to criticize lack of consistency, then what we have now is much less consistent, obviously, than the Morrison-Gettleman that's in the stratiform codes. I mean, they'd be much closer in terms of being consistent, even with what is in that code right now. I don't know what it would take. Ideally, the science would be brought up to date as well, but we'd still be much more compatible than we are at the present time, given the microphysics that's currently in the Zhang-McFarland scheme. This would be a case, I think, of letting the perfect maybe be the enemy of the good, to say the science isn't quite compatible in these two schemes yet.
Well, I think it's a good direction. I mean, I think it's something very concrete we can start doing. And yeah.
And I think I do struggle to sort of control the high clouds, and I think that would provide us some degrees of freedom there. Because when we're messing with club parameters, we're pretty much entirely aiming it at low clouds, and I think it would be a mistake to just force ourselves just to only consider that.
All right. So if there's
So I'll just
go ahead, Adam.
I was just going to mention the next bullet point on time step sensitivity. I'm actively engaged in improving how the time stepping between club and MG are done right now.
Right.
And Huey Wan's dribbling approach is something that we have on the docket to explore. And I'm fairly optimistic about the dribbling in the state to the subcycles as a better approach to shocking the first subcycle with the entire state update.
Sean has his hand up.
Yeah, I just wanted to say that I think Hui has found even more than what she presented last year that there is certainly a change to the radiative cooling when you're doing the dribbling that where it's actually a pretty wide range of circumstances where it makes a difference. I'd also say the way that MG2 is coupled to club is not really the same because they're sub-step together. So it's the way that the microphysics is coupled in, it's sort of irrelevant, but the radiation and the dynamics tendencies would be affected by this dribbling approach.
Is she giving a talk this week or no?
I don't remember her name on the agenda, so I think not.
So we have a big meeting with her next week, a long meeting, to go over the code mods. So it's on the docket.
All right.
You're in that meeting, Julio, just so you know.
Okay. I'm not going anywhere. All right. So I think it's already it's past 3:30. I think it's been a relatively long day. If people want to, last chance to chime in today. We will have more discussions tomorrow and on Thursday. I think there's a plan. I think we are going to be starting 15 minutes. Elizabeth, could you update me? I'm not quite sure what's happening tomorrow morning for the middle atmosphere ozone and dynamics session.
Yeah, we're going to start at 9:15.
Okay, all right.
Yep, we're just Doug Kinnison's dropped out to give his talk, so we'll just figured we'd give everybody an extra 15 minutes in the morning.
Okay. All right then. So I think we'll thanks for everybody.